Look up at the night sky, past the familiar points of light from nearby stars, past the hazy band of our own Milky Way, and journey with your mind to the very edge of everything we know. Out there, in the profound and ancient darkness, exist beacons of almost unimaginable power, celestial objects so brilliant they can outshine entire galaxies, yet so distant we are seeing them as they were when the universe was in its swaddling clothes. These are the most distant quasars, and the light arriving at our telescopes today began its voyage when the cosmos was a mere fraction of its current age. It's a thought that can send a shiver down your spine. We are essentially looking back in time, witnessing the universe's fiery, tumultuous youth. What are these cosmic lighthouses shining from the edge of time itself, and what profound secrets do they hold about our universe's chaotic infancy? Their story is not just one of distant, abstract phenomena. It is the origin story of everything, including us. Today, we are embarking on a monumental journey to explore 50 incredible facts about these most distant quasars. Think of this as the ultimate cosmic detective story, where each fact we uncover is a vital clue, a piece of a grand puzzle that stretches across billions of light years. These are not just random bits of trivia. They are the keys to understanding how the first supermassive black holes came to be, how the fog of the early universe was burned away, and how the seeds for galaxies like our own were first planted. We will venture into a realm of extremes where gravity warps spacetime into knots and matter, spiraling into oblivion, blazes with the energy of a trillion suns. This is an adventure into the deepest archives of the cosmos, reading a history written in light that has traveled for eons just to reach our curious eyes. So prepare to have your perspective on reality stretched. We are about to dive into the science, the mystery, and the sheer awe-inspiring nature of these objects. From their mind-bending distances and colossal energies to the revolutionary telescopes that allow us to find them, every fact will bring us closer to answering fundamental questions about where we came from and how this magnificent universe came to be. This is a story of cosmic giants, of ancient light, and of humanity's relentless, beautiful curiosity to understand its place in the vastness of space and time. Let's begin our countdown and unlock the universe's greatest mysteries, one astonishing fact at a time. And so we arrive at our very first fact, a cornerstone for understanding everything that follows. Fact number 1: quasars are the ultra-bright cores of young galaxies. It's a simple statement, but one that holds a universe of meaning. The name itself is a bit of a clue. Quasar is short for quasi-stellar radio source because when they were first discovered, they appeared as star-like points of light in optical telescopes, yet they emitted powerful radio waves. We now know they are anything but stars. A quasar is, in essence, the spectacularly luminous heart of a galaxy that is going through a tremendously active and violent growth spurt. This brilliant core is scientifically known as an active galactic nucleus, or AN, and its power source is one of the most extreme objects in the cosmos, a supermassive black hole. Now, a black hole itself is dark, and region of spacetime where gravity is so intense that not even light can escape. So, how does something defined by its darkness become the universe's most brilliant beacon? The answer lies not in the black hole itself, but in the frenzied activity just outside its point of no return, the event horizon. As vast clouds of gas, dust, and even entire stars are pulled in by the black hole's immense gravity, they don't just fall straight in. Instead, they form a swirling, flattened, and incredibly hot whirlpool of matter called an accretion disk. Think of water spiraling down a drain, but on a cosmic scale and heated to temperatures of millions of degrees. This unimaginable heat, generated by friction and tremendous gravitational forces, causes the material in this disk to glow with a ferocious intensity, radiating energy across the entire electromagnetic spectrum, from radio waves to visible light to powerful X-rays. This is the engine of the quasar, a cosmic powerhouse where the conversion of gravitational energy into light is so efficient it can outshine the combined light of every single star in its host galaxy. Therefore, when astronomers train their telescopes on the most distant quasars, they are performing a kind of cosmic archaeology. They are looking past the dim, faint halo of the young galaxy itself and staring directly into its brilliant, raging core. We are witnessing a galaxy in its most formative and volatile stage, a time when its central black hole is feasting on a bounty of surrounding material, announcing its presence across the cosmos with a lighthouse beam of pure energy. This violent phase doesn't last forever. Eventually, the black hole consumes or blows away the nearby fuel supply, the dazzling accretion disk fades, and the quasar goes quiet, leaving behind a dormant supermassive black hole like the one that resides quietly at the center of our own Milky Way today. So, every distant, brilliant quasar we see is a snapshot of a galaxy's wild youth, a temporary but spectacular era of cosmic construction and destruction. This brings us to our second astonishing fact, a concept that fundamentally reshapes how we perceive the night sky. The most distant quasars are also the youngest. This statement seems to defy common sense at first glance. How can something farther away be younger? The key lies in the nature of light itself and the vast, expanding fabric of the cosmos. Light, while incredibly fast, travels at a finite, set speed. It takes time to cross the immense gulfs between celestial objects. When we look at the sun, we see it not as it is now, but as it was about 8 minutes ago, the time it takes for its light to reach us. When we gaze at the Andromeda Galaxy, we are witnessing it as it appeared 2.5 million years in the past. Now, stretch this idea to its absolute extreme. When our most powerful telescopes detect a quasar that is 13 billion light-years away, the light entering the camera's lens has been on an uninterrupted journey through the universe for 13 billion years. We are not seeing that quasar as it exists today. We are receiving a photon fossil, an image from a time when the universe itself was in its infancy. Given that the current best estimate for the age of the universe is about 13.8 billion years, these most distant quasars show us a cosmos that was less than 1 billion years old. We are observing an era when the universe was a mere 7% of its current age, a cosmic toddler taking its first formative steps. This transforms every distant quasar from a simple object in space into a profound time capsule. They are not just out there, they are back then. Each one is a direct window, a snapshot frozen in time, allowing us to study the raw and primitive conditions of the early universe in a way that no simulation or theory ever could. This was a period of cosmic history known as the Dawn Era, a time following the darkness after the Big Bang's initial glow had faded. The universe was a simpler, denser, and much darker place, filled with opaque fog of neutral hydrogen gas. Then something happened. The first stars and galaxies ignited, and with them, the first quasars flared into existence, their intense radiation beginning to burn away the cosmic fog in a process called reionization. By studying the light from these ancient quasars, astronomers can analyze how its spectrum has been altered by passing through that primordial hydrogen gas, effectively taking the temperature and measuring the composition of the early cosmos. The significance of this cannot be overstated. These distant beacons allow us to witness firsthand the assembly of the very first large-scale structures in existence. We are watching the birth of the very first supermassive black holes and the chaotic, violent construction sites of the earliest galaxies that would eventually evolve into the majestic spirals and ellipticals we see in our local universe today. Every piece of data gleaned from their light is a clue in the ultimate cold case. How did our universe, from a hot, dense beginning, evolve into the complex, structured, and beautiful cosmos we call home? These quasars are the lighthouses guiding us through the fog of time, illuminating the very first chapters of our cosmic story. Building directly on that idea of looking back in time, we come to a discovery so baffling that it challenges our fundamental understanding of cosmic evolution. Fact number 3. These most distant quasars host supermassive black holes of such immense size that they defy all logical expectations. We're not talking about large black holes, we are confronting absolute behemoths. At the heart of these ancient, brilliant cores, astronomers have found black holes with masses reaching billions of times that of our own Sun. To put that into perspective, the supermassive black hole at the center of our Milky Way, Sagittarius A star, is a relative lightweight at about 4 million solar masses. The black holes powering the earliest quasars are often 1,000 times more massive, and they achieved this staggering size when the cosmos was barely out of its infancy. This presents science with one of the most compelling puzzles in modern cosmology, a true cosmic chicken and egg problem. How did these gravitational monsters grow so unimaginably large so quickly? The universe after the Big Bang was a fairly uniform soup of hydrogen and helium. For a black hole to reach a mass of over 1 billion suns by the time the universe is only 700 or 800 million years old, it would have had to consume matter at a ferocious, breakneck pace, pushing right up against the theoretical limits of physics for its entire existence. It's like discovering a fully grown, 50-foot-tall toddler. The sheer scale and speed of this growth seems to violate our models of how these objects form and feed. So how could this happen? Astronomers are actively investigating several compelling, though still theoretical, pathways. One leading idea is known as direct collapse. In this scenario, the first generation of structures weren't small stars, but instead enormous, pristine clouds of gas that collapsed under their own weight directly into a massive black hole seed, bypassing the star formation stage entirely. These initial seeds could have been immense from the very start, perhaps tens or even hundreds of thousands of times the mass of the Sun, giving them a colossal head start on their growth. Another theory involves a rapid, frantic period of merging and feeding. The early universe was a much denser, more chaotic place, and smaller black hole seeds from the first stars could have merged together repeatedly and gorged on the abundant surrounding gas at an incredible rate, a feeding frenzy on a cosmic scale. We can make this abstract problem concrete by looking at a specific, record-breaking example, the quasar known as J0313-1806. This object is so distant we see it as it was when the universe was a mere 670 million years old. Yet at its heart lies a supermassive black hole with a measured mass of over 1.6 billion suns. For this single object to exist at that point in cosmic history, its progenitor seed must have been in place incredibly early and feasted almost continuously at its maximum possible rate. Its very existence forces us to reconsider the conditions in the primordial cosmos, suggesting that some regions must have been far more fertile and dynamic for black hole growth than we ever previously imagined. This isn't just a distant curiosity, it's a fundamental challenge that pushes the boundaries of physics and compels us to rewrite the story of how the most massive structures in the universe first came to be. This staggering growth leads directly to an equally staggering output of energy, which brings us to fact number 4. The sheer, raw luminosity of a quasar is so immense that it can outshine its entire host galaxy by a factor of thousands. Let that number sink in for a moment. Our own Milky Way galaxy is a sprawling cosmic metropolis, home to several 100 billion stars, each a sun like our own, along with vast clouds of glowing gas and dust. The combined light of all these stars creates the soft, hazy band we see arching across the night sky. Now, imagine a single, tiny point at the galaxy's center, a region not much larger than our solar system, blazing with a ferocious intensity that drowns out the light of every one of those hundreds of billions of stars. That is the awesome power of a quasar. It is the ultimate cosmic spotlight, so brilliant that the galaxy it calls home is reduced to a faint, ghostly smudge in its overwhelming glare. This incredible luminosity is not just a fascinating trivia point. It is the very property that makes quasars, especially the most distant ones, observable at all. They function as nature's ultimate beacons, piercing the cosmic darkness and allowing us to see them from the farthest reaches of space and time. A helpful way to visualize this is to think of a powerful lighthouse on a remote, rocky coast. On a dark, foggy night, the island the lighthouse sits on might be completely invisible, shrouded in shadow and mist. But the lighthouse beacon itself cuts through the gloom, a brilliant, focused needle of light that can be seen from dozens of miles away. In this analogy, the dim, sprawling island is the quasar's host galaxy, and the intensely bright lighthouse is the quasar's active nucleus. From our vantage point billions of light years away, we can easily detect the brilliant beacon long before we can make out the faint outline of the island it stands upon. How is such an unimaginable output of energy even possible? The answer takes us back to the physics of the accretion disk. As matter spirals inward at velocities approaching the speed of light, it is subjected to unimaginable gravitational and frictional forces, heating it to temperatures of millions of degrees. This superheated plasma doesn't just glow, it radiates energy with an efficiency that dwarfs all other known processes. Nuclear fusion, the power source of stars, converts only about 0.7% of mass into energy. In the extreme gravity well around a supermassive black hole, the conversion of gravitational energy into radiation can be up to 40 times more efficient. This engine is so potent that the light and radiation it produces can exert an outward pressure, actually pushing surrounding gas and dust away and effectively regulating the black hole's own growth. This creates powerful galactic winds that can blow away the star-forming material in a galaxy, potentially shutting down its own development. So, a quasar is not merely a bright light. It is an active, dominant force that can shape the entire evolution of its galactic home, a testament to the fact that the brightest objects in the cosmos are also some of the most influential. Now, this incredible journey of light across billions of years comes with a fascinating and fundamental side effect, leading us to fact number 5. The light from these most distant quasars is dramatically stretched into the infrared part of the spectrum. This phenomenon is not a flaw or an error. It is one of the most crucial pieces of evidence we have for an expanding universe and our primary tool for measuring these mind-boggling distances. The concept is known as redshift, and it works similarly to the way the sound of a passing ambulance siren changes pitch. As the ambulance moves away from you, the sound waves are stretched out, making the siren's pitch sound lower. Light behaves in an analogous way. As a quasar's light travels through the expanding fabric of space, the very wavelengths of that light are stretched out, causing them to shift toward the red, and ultimately the infrared end of the electromagnetic spectrum. The greater the distance the light has to travel, the more the universe has expanded during its journey, and the more extreme this redshift becomes. For the very first quasars, the effect is so profound that the light which was originally emitted as visible and even ultraviolet radiation has been stretched by the expansion of space into the infrared by the time it finally reaches us. This has a direct and practical consequence for astronomers. If we tried to observe these ancient beacons with only telescopes designed to see visible light, like our own eyes, we would see nothing at all. The quasars would be completely invisible, their vital light having been shifted into a part of the spectrum we cannot perceive. The most distant objects in the universe are quite literally hidden from our natural sight by the expansion of the cosmos itself. This is precisely why the launch of the James Webb Space Telescope marked such a revolutionary moment in cosmology. Unlike the Hubble Space Telescope, which was optimized for visible and ultraviolet light, Webb was specifically designed as a powerful infrared observatory. It is, in essence, the perfect machine for reading these cosmic red-shifted letters. Where Hubble might see an empty patch of sky, Webb peers deep into the infrared and reveals brilliant quasars shining from the edge of time. By carefully analyzing the exact amount of redshift in a quasar's light, astronomers can precisely calculate its distance and therefore how long its light has been traveling, effectively determining its place in cosmic history. This allows us to create a timeline of when the first quasars ignited and how they evolved, turning a curious optical effect into the most reliable cosmic yardstick we have. This stretching of light does more than just tell us how far away something is. It also alters the story the light can tell. Certain telltale fingerprints in a quasar's spectrum, specific absorption lines that act like a barcode, are used to study the composition of the primordial gas the light passed through on its way to us. Extreme redshift means these barcodes are themselves stretched and shifted, requiring specialized instruments to decode them correctly. Without the ability to see in the infrared, we would be missing the light from the most formative epoch of galaxy formation. The expansion of the universe, which hides these distant quasars from our eyes, is the very reason we need tools like Webb to uncover them, revealing a universe that is both fleeing from us and, through our ingenuity, revealing its deepest secrets. This history of discovery brings us to a pivotal and wonderfully human chapter in our story. Fact number 6. The most distant quasars were initially mistaken for something much more ordinary, earning them the name quasi-stellar stars. Their journey into the scientific consciousness began not with a grand revelation, but with a puzzle. In the late 1950s and early 60s, as radio astronomy was hitting its stride, astronomers began cross-referencing powerful radio wave sources with visible light photographs of the sky. They expected to find these radio emissions coming from nearby galaxies or strange nebulae, but for a handful of these sources, the optical counterpart was not a fuzzy patch of light. It was a single, sharp, star-like point. This was deeply confusing. Stars, as a rule, are not powerful emitters of radio waves, so what were these objects? They were dubbed quasi-stellar radio sources, a name that perfectly captures their perplexing nature. They looked like stars, but their radio emission said they were something else entirely. The name was quickly shortened to the snappier quasar, a term that has stuck ever since. The true mystery, however, lay in their light. When astronomers finally managed to capture the spectrum of one of these quasi-stellar points, the data was even more baffling. A spectrum is like a celestial object's fingerprint, with dark and bright lines that reveal the chemical elements present. The spectra of these quasars showed strong, broad emission lines, but they didn't match the signature of any known element. It was as if these objects were made of a completely unknown substance, something not found anywhere else in the universe. For a time, these unrecognizable lines fueled wild speculation. Were they from exotic matter? Was our understanding of physics itself incomplete in some fundamental way? The scientific community was grappling with a genuine cosmic enigma, a riddle written in light from across the universe. The breakthrough, the brilliant eureka moment, came when the astronomer Martin Schmidt was studying the first identified quasar, known as 3C273. He was staring at its strange spectrum with its set of mysterious, prominent lines when he had a sudden, revolutionary insight. What if these lines weren't from some unknown element? What if they were, in fact, the very familiar lines of common hydrogen, but shifted so far toward the red end of the spectrum that they had become completely unrecognizable? He tested the idea, and the pieces of the puzzle clicked into place with stunning force. The lines were indeed from hydrogen, but they were redshifted by an amount previously thought impossible for a single object. The calculated velocity implied 3C273 was receding from us at a staggering 16% of the speed of light. Applying Hubble's law, this meant the object was billions of light years away. This realization was nothing short of earth-shattering. That a single star-like point could be so unimaginably distant meant it had to be emitting almost inconceivable amounts of energy to appear as bright as it did from Earth. In one brilliant stroke, the mystery of the strange spectra was solved, and in its place, an even greater mystery was born. What physical process could possibly generate such staggering luminosity? The term quasar had stuck, but its meaning was transformed. These were not strange stars at all. They were the impossibly bright cores of incredibly distant galaxies, their light stretched by the expansion of the universe itself. This discovery didn't just solve a puzzle, it flung open a new window on the cosmos, revealing an universe far more vast, dynamic, and violent than anyone had previously dared to imagine. It was the moment we realized that the quiet, steady stars in our sky were hiding a secret, brilliant, chaotic beacons shining from the edge of space and time. Now, with that history of discovery in mind, let's turn our attention to the current superstar in this cosmic distance race. Fact number 7 introduces us to the reigning champion, the quasar known as J0313-1806. This is not just any distant object, it is the most distant quasar humanity has ever found, a title it holds for pushing our observational capabilities to their absolute limit. We see this quasar not as it is today, but as it appeared when the cosmos was a mere 670 million years old. To put that youth into perspective, that's like looking at a photograph of a person on their first birthday. If the person were the entire universe and its lifespan was nearly 14 billion years. The light from J0313-1806 has been journeying through the expanding cosmos for over 13 billion years just to tell us this story from the dawn of time. But its incredible distance is only half of what makes this object so astonishing. The true shock lies in the properties we've been able to measure. At the furious heart of this ancient beacon resides a supermassive black hole of almost incomprehensible scale, with a mass calculated to be 1.6 billion times that of our Sun. Let's try to grasp the sheer immensity of that number. If you were to take every single star in our entire Milky Way galaxy, all several hundred billion of them, and combine them into one colossal object, you would still only have about half the mass of this single, voracious black hole that existed when the universe was in its infancy. The fact that such a gravitational titan could assemble itself so quickly after the Big Bang is the central, beautiful mystery that this quasar presents to science. Its power output is equally difficult to fathom. The luminosity of J0313-1806 is so staggering that it outshines our own Sun by many trillions of times. Imagine taking every bit of sunlight that falls on Earth, every ray that warms a desert or sparkles on an ocean, and then multiply that energy by trillions upon trillions. That is the continuous, ferocious output flowing from a region of space not much larger than our solar system. This isn't just a bright light, it's a cosmic blowtorch, a testament to the most efficient and violent energy generation process known to exist in nature, fueled by matter plunging toward the event horizon at nearly the speed of light. The discovery of this record holder, however, is not the end of the story, but rather a thrilling milestone in an ongoing quest. Astronomers around the world are in a constant, relentless hunt for the next champion, for a quasar that lies even further back in time. Every new observatory, like the James Webb Space Telescope, acts as a bigger and more sensitive net cast into the cosmic ocean, with the potential to snag an even more distant and ancient specimen. The discovery of J0313-1806 didn't solve the puzzle of early black hole growth. It sharpened it, forcing theorists to refine their models of direct collapse and hyper-efficient feeding. Finding a quasar from a time when the universe was only 500 million years old or even younger would put our current theories to an even more severe test. Each new record breaker is a data point that defines the very limits of what was possible in the early universe, revealing the conditions under which the first cosmic structures could rise from the primordial darkness. This quasar is the current frontier, but the hunt for its predecessors continues, promising to illuminate the very moment when the first supermassive black holes began to ignite and fundamentally reshape the cosmos. This brings us to a fact that truly grounds the cosmic scale of these discoveries in a tangible, almost poetic reality. Fact number 8. The light from the most distant quasars has been traveling for billions of years to reach our telescopes. We use numbers like 13 billion light-years so often in astronomy that they can start to feel abstract, just another large figure. But let's pause and genuinely feel the weight of that journey. For a photon of light leaving a quasar 13 billion years ago, its voyage began in a universe that was radically different from the one we inhabit today. The cosmos was smaller, hotter, and denser. Our Sun, our Earth, our entire solar system would not even begin to form for another 8.5 billion years. That light was already ancient, having crossed half of cosmic history by the time the first single-celled organisms appeared on our planet. We are, in the most literal sense possible, receiving a message from the cosmic dawn. Every flicker of light captured by the James Webb Space Telescope from such an object is a direct signal from an era when the first grand structures were lighting up the darkness. That photon has traveled across an ever-widening gulf, passing through proto-galaxies and vast, empty voids, its wavelength being stretched all the while by the relentless expansion of space itself. It is a cosmic marathon runner, carrying within its specific energy the only first-hand account of what the universe was like in its extreme youth. By the time this ancient light finally lands on a detector here on Earth, the quasar that emitted it may have long since faded, its brilliant accretion disk consumed and its central black hole grown quiet, the galaxy around it having matured into something unrecognizable from its violent beginnings. This concept fundamentally changes our relationship with the night sky. We are not looking at a static museum display. We are watching a live broadcast from the distant past, but on a cosmic delay so immense it encompasses the entire history of our planet. We can observe the light from a quasar that shone when the universe was only 700 million years old, yet we have no way of knowing what that object has become in the intervening 13 billion years. It forces upon us a profound humility. Our entire human history, from the first civilizations to the modern age, is less than a blink of an eye compared to the travel time of this light. All of our triumphs and tragedies have occurred while this single beam of energy was in transit, completely oblivious to our world. The sheer scale of astronomical time reminds us that the universe operates on a clock utterly different from our own. And these distant quasars offer us the rarest of gifts, a chance to look directly into the pages of a history book written not in ink but in the very fabric of space-time and light. Now, this brings us to a fact that seems to defy the very definition of these cosmic lighthouses. Fact number 9. The most distant quasars, despite being fixed landmarks in the cosmos, can exhibit tiny, measurable motions across the sky. The idea seems almost paradoxical. We've established that these objects are so incredibly far away that they should be completely stationary from our vantage point, like a mountain on the horizon that never seems to move no matter how far you travel. And for the most part, they are. Their proper motion, their actual movement through space is negligible over human timescales. Yet, with the incredible precision of modern instruments like the Gaia Space Observatory, astronomers have detected minuscule shifts in the positions of some quasars. This isn't a mistake in the data, it's a real physical effect that opens a fascinating new window into their nature. So, if the quasars themselves aren't actually zipping around, what could possibly be causing this subtle celestial dance? The answer lies not in the quasar's own motion, but in the intricate interplay of light and gravity along its billion-year journey to Earth. One of the primary culprits is a phenomenon known as gravitational microlensing. Imagine a solitary, dark object drifting through the halo of our own Milky Way, something like a rogue planet, a brown dwarf, or even a stellar mass black hole that emits no light of its own. As this invisible mass moves through space, it can, purely by chance, pass directly between us and a distant quasar. According to Einstein's theory of general relativity, the gravity of this intervening object acts like a lens, bending and distorting the quasar's light. As the lensing object moves, it slightly shifts the apparent position of the quasar in the sky, creating the illusion that the quasar itself is moving. It's a cosmic sleight of hand where a dark, unseen object in our own galactic backyard puppeteers the image of a beacon from the edge of time. But there's another, even more intriguing source for this motion that originates from the quasar itself. Think back to the furious accretion disk, that superheated whirlpool of matter spiraling into the black hole. This disk isn't a rigid, flat plate, it's a dynamic, chaotic structure. Intense magnetic fields and relativistic effects can cause the inner parts of the disk to wobble or precess over time, much like a spinning top slowly tracing a circle as it winds down. This precession isn't a physical movement of the entire quasar through space, but a shift in the orientation and geometry of its brilliant engine. As the disk wobbles, the region emitting the most light effectively moves, causing the overall bright spot we observe to appear to jitter in a tiny, predictable pattern. By meticulously tracking this motion, astronomers can indirectly map the structure and behavior of the accretion disk itself, learning about its stability, its magnetic field, and the extreme physics happening just outside the event horizon. The true power of measuring these minuscule shifts lies in the wealth of information they unlock. A microlensing event is not just a curiosity, it's a free laboratory for studying dark, isolated objects in our galaxy that we would have no other way of detecting. By analyzing how the quasar's light is shifted and magnified, we can estimate the mass of the invisible lensing object, helping to census the population of these dark wanderers. Meanwhile, the precessional wobble of the accretion disk serves as a direct probe of the black hole's spin and the immense gravitational forces at play. Each tiny, measured motion is a clue, a piece of data that helps us understand everything from the distribution of matter in our own galaxy to the fundamental dynamics of gravity's strongest grip. It's a remarkable testament to human ingenuity that we can not only detect a flicker of light from 13 billion years away, but also measure its subtle shiver, using that tremor to illuminate the dark corners of the cosmos and the violent hearts of the universe's first giants. Now, all this talk of quasars outshining galaxies naturally leads to a fundamental question: where does all this staggering energy actually come from? This brings us to fact 10, a core principle of astrophysics. Quasars are ultimately powered by gravitational energy. We often simplify this by saying a supermassive black hole is eating, but that casual phrase hides a process of breathtaking power and efficiency. The true engine is the conversion of gravitational potential energy into pure radiation, a mechanism that dwarfs every other known power source in the universe. To understand how this works, let's follow a single lump of gas on its final, fateful journey. Far out in the galaxy, this gas possesses a certain amount of gravitational potential energy simply by virtue of its distance from the central black hole. Think of it like a rock perched at the top of a very, very deep well. As the gas begins to fall inward, pulled by the black hole's immense gravity, it trades that stored potential energy for speed, accelerating to a significant fraction of the speed of light. But it doesn't simply plunge straight in. Instead, it joins a vast, chaotic traffic jam of other infalling material, all swirling into a flattened, superheated structure called an accretion disk. This is where the magic happens. As these hypervelocity particles of gas and dust slam into each other within the disk, they create an incredible amount of friction. The same kind of friction that warms your hands when you rub them together, but amplified to an almost unimaginable extreme. This frictional heating, combined with the mind-bending stresses of tidal gravity, raises the temperature of the accretion disk to millions of degrees. At these temperatures, the matter doesn't just glow, it becomes a searing plasma that radiates intensely across the entire electromagnetic spectrum, from radio waves up to lethal gamma rays. The entire disk transforms into a brilliant celestial dynamo, and the light we see from a quasar is the visible manifestation of this ferocious release of gravitational energy. The most astounding part of this whole process is its sheer efficiency. Let's compare it to the power source of stars, which is nuclear fusion. In the core of a star like our Sun, the process of fusing hydrogen into helium converts only about 0.7% of the mass involved into energy. It's a powerful process, to be sure, but it's also somewhat frugal with its fuel. In the intense gravitational field just outside a black hole's event horizon, however, the conversion of mass into energy is radically more effective. The physics of general relativity allows this process to reach efficiencies of up to 40%. That means for every 10 kilograms of material that spirals into the accretion disk, the equivalent of 4 kilograms is transformed directly into pure radiant energy. This is why a quasar can outshine a galaxy full of stars. Its engine is simply in a different league, operating on a level of productivity that makes stellar fusion look almost inefficient. This gravitational powerhouse is the reason these distant beacons can serve as cosmic lighthouses, their light cutting across billions of light years to tell us the story of the universe's most energetic and transformative events. And this brings us to a profound truth about the cosmos. Nothing lasts forever, not even the brilliant reign of a quasar. Fact 11. Quasars can and do turn off and become dormant. These cosmic beacons are not permanent fixtures in the sky. They are actually a fleeting, albeit spectacular, phase in the life of a galaxy. The key to this transformation lies in the availability of fuel. A quasar's brilliance is entirely dependent on a continuous and abundant supply of gas, dust, and stars to feed its central black hole. This material forms the accretion disk, and without it, the entire luminous engine simply shuts down. Think of a quasar as a gigantic cosmic bonfire. For it to blaze with incredible intensity, you need to keep throwing enormous amounts of wood onto the flames. In a galaxy's youth, fuel is often plentiful. It might be consuming vast reservoirs of primordial gas, or perhaps a major merger with another galaxy has funneled a tremendous amount of fresh material toward the center, igniting a brilliant quasar phase. However, this frantic feeding cannot be sustained indefinitely. Eventually, the black hole will consume most of the readily available fuel in its immediate vicinity. Furthermore, the quasar itself often contributes to its own demise. The intense radiation and powerful particle jets blasting out from the core can exert an outward pressure, effectively blowing the remaining gas and dust far out into the galactic halo or even completely out of the galaxy. This process, known as feedback, acts like a powerful wind that scatters the very fuel the black hole needs to survive, snuffing out the fire from within. Once the accretion of matter slows to a trickle or stops altogether, the dazzling accretion disk fades from a searing, radiant powerhouse to a dim, quiet structure. The brilliant quasar shuts down and the active galactic nucleus becomes dormant. The supermassive black hole, however, does not disappear. It remains at the galaxy's center, a silent gravitational titan, but now it is a sleeping giant. It's like the difference between a raging forest fire and a pile of hot embers. The potential for fire is still there, but without new fuel, it sits dormant. A perfect example of this is right here in our cosmic neighborhood. The supermassive black hole at the center of our own Milky Way, Sagittarius A star, is a perfect example of a dormant quasar engine. It has a mass of over 4 million suns, yet it emits only a tiny, faint trickle of radiation compared to its brilliant ancestors. It is quiet, having long ago consumed or cleared out the material in its immediate vicinity. This life cycle has a staggering implication for our understanding of galaxy evolution. It suggests that many, if not all, of the large, stately galaxies we see in the universe today, including our own Milky Way, likely hosted a violent, brilliant quasar in their distant past. Every majestic spiral and giant elliptical we observe may have once been the scene of a spectacular, energetic fireworks display at its core. Our home galaxy, now a relatively calm and orderly spiral, was probably once a blazing beacon, its central black hole in a ferocious feeding frenzy that shaped its early development. The dormant black holes we find at the hearts of nearby galaxies are not anomalies. They are the retired engines of ancient quasars, the silent remnants of a galaxy's wild and brilliant youth. This connects us directly to the most distant objects in the universe. The brilliant quasars we see at the edge of time are not some exotic, unrelated phenomenon. They are the youthful versions of the galaxies, including our own, that fill the cosmos today. We are essentially looking back at our own galaxy's fiery beginnings. This incredible release of gravitational energy doesn't just produce light. In many cases, it also forges one of the most spectacular and violent structures in the entire cosmos. Fact 12. The most powerful quasars can emit colossal, focused jets of plasma that blast their way across intergalactic space. While the accretion disk radiates energy in all directions, a significant portion of a quasar's power can be channeled into two narrow, opposing beams that erupt from the poles of the system. These are not gentle streams, they are relativistic jets, so named because the ionized gas within them is accelerated to velocities approaching the speed of light itself. The formation of these jets is a direct result of the complex, twisted physics happening right at the black hole's doorstep. The intensely hot accretion disk is threaded with unimaginably powerful magnetic fields. As the disk spins, it drags these magnetic field lines with it, winding them up into a tightly coiled, rotating structure that acts like a colossal natural particle accelerator. Near the black hole's poles, where the magnetic field is most concentrated and the path of least resistance exists, this twisted magnetic slingshot can launch charged particles outward in two oppositely directed beams. The exact mechanism is still an area of active research, but it likely involves the black hole's own spin transferring enormous rotational energy to the surrounding plasma, funneling it into these incredibly narrow and stable corridors of power. The scale of these jets is almost impossible to comprehend. They can extend far beyond the bounds of their host galaxy, stretching across hundreds of thousands or even millions of light years into the emptiness of intergalactic space. To visualize this, imagine a structure so long that it could reach from our Milky Way to the Andromeda Galaxy and keep going for dozens of times that distance. These jets are often only visible to radio telescopes, as the electrons spiraling along the magnetic fields within them emit a characteristic glow in the radio part of the spectrum. The most stunning images from observatories like the Very Large Array show these cosmic blowtorches as long, thin filaments, often punctuated by bright, lumpy regions where the jet has collided with a denser patch of intergalactic gas. When this supersonic jet slams into the tenuous material that exists between galaxies, it doesn't just slow down quietly. It creates a cosmic traffic jam of epic proportions, plowing into the gas and piling it up into massive, ballooning structures known as radio lobes. These lobes are gigantic cavities of hot, magnetized plasma that glow intensely at radio wavelengths. They act as a vast reservoir, storing the immense energy pumped into them by the jet over millions of years. This process represents a colossal transfer of energy from the tiny central engine out into the galactic environment on a truly intergalactic scale. The jets and their resulting lobes are a dramatic example of how a quasar, a phenomenon confined to a region smaller than our solar system, can reach out and influence the cosmos on the very largest scales, shaping the future of galaxy clusters and regulating the flow of gas that will one day form new generations of stars. These jets are the ultimate signature of a quasar's power, a visible testament to the fact that the universe's most energetic events are capable of writing their history across millions of light years of empty space. Of course, the story of these distant giants is woven into the very history of their discovery, and no object is more central to that narrative than the one that started it all. Fact 13 takes us back to a pivotal moment in astronomical history. The first quasar ever identified was the brilliant object known as 3C273. Before this discovery, the cosmos seemed a slightly more familiar and predictable place. But 3C273, a seemingly unremarkable point of light in the constellation of Virgo, was about to shatter that perception and redefine our understanding of the universe's scale and violence. Its journey to recognition began with the burgeoning field of radio astronomy. In the early 1960s, astronomers were diligently cataloging cosmic radio sources, and the third Cambridge catalogue listed this particular source as number 273. When they pointed optical telescopes at its coordinates, they saw what appeared to be a faint blue star. But this was deeply puzzling because ordinary stars simply do not emit such powerful radio waves. It was a celestial impostor, a quasi-stellar radio source that defied easy classification. For a time, it remained an enigma, a single point of light hiding an incredible secret. The true breakthrough came in 1963, when the brilliant astronomer Martin Schmidt was studying a photograph of 3C273's spectrum. He saw a series of prominent emission lines, but they were in all the wrong places, not matching the signature of any known element. Staring at this pattern, he had a flash of pure genius. What if these weren't unfamiliar lines from a new substance, but were instead the most familiar lines of all, those of hydrogen, shifted dramatically toward the red end of the spectrum by an unprecedented amount? When he calculated the implications, the result was staggering. The redshift indicated that 3C273 was not a nearby star at all, but an object fleeing from us at nearly 16% the speed of light and located an incredible 2.4 billion light-years away. This single realization was the key that unlocked the entire mystery of quasars. In one brilliant stroke, Schmidt solved the riddle of the strange spectra and simultaneously revealed the existence of objects of almost unimaginable luminosity. For a single star-like point to be visible from such a distance, it had to be shining with the power of hundreds of galaxies. The name quasar was born from this moment, and the field of active galactic nuclei was open for exploration. 3C273 became the prototype, the Rosetta Stone that taught astronomers how to read the language of cosmic distances and energies, forever changing our perception of the universe from a relatively calm place to one filled with unimaginable, violent brilliance. What makes 3C273 so valuable even today is its paradoxical nature. While 2.4 billion light-years is an almost incomprehensible distance in the grand hierarchy of quasars, it is actually one of our closest and brightest neighbors. This proximity is a gift to science, as it allows for a level of detailed study impossible with its more distant cousins. With the resolving power of the Webb Space Telescope, astronomers have been able to do what was once unthinkable. They have peeled back the overwhelming glare of the central point and clearly revealed its host galaxy. It turns out to be a giant elliptical galaxy, a vast collection of ancient stars, and the quasar itself is a blazing pinpoint at its very center. This direct observation provides a stunning visual demonstration of a quasar's raw power. Even at this relatively mature cosmic age, a time when the universe was already rich with evolved galaxies, the central engine of 3C273 still dramatically outshines the combined light of its hundreds of billions of stars. It is the ultimate proof of concept, a living laboratory showing us that the supermassive black hole phenomenon is not just a feature of the distant past, but an active, ongoing process. By studying this nearby, brilliant example, we gain profound insights into the physics that must govern even the most far-flung quasars at the edge of time. 3C273 is more than just a historical footnote. It is a constant reminder that the most profound discoveries often begin with a single, puzzling point of light that refuses to fit into our existing understanding of the cosmos. This remarkable ability of quasars to illuminate the unseen brings us to a truly profound application. Fact 14. These distant beacons are absolutely crucial for mapping the cosmic web. We often picture the universe as a collection of galaxies scattered through a vast, empty void, but that's not the complete picture. Galaxies are actually strung along a colossal, intricate network of invisible threads and sheets of dark matter and diffuse gas, a structure astronomers call the cosmic web. This web is the largest pattern in nature, the fundamental scaffolding upon which the entire universe is built. The problem is, the vast majority of this structure is made of incredibly thin, dark gas that doesn't produce any light of its own, rendering it completely invisible to our telescopes under normal circumstances. So how do you map something you cannot see? You use the most powerful flashlights in the universe, quasars. The technique works like a sophisticated version of using a car's headlights in a dense fog. You can't see the fog itself in the darkness, but when your bright headlights shine through it, the tiny water droplets in the air scatter and absorb some of the light, creating a visible beam and revealing the fog's presence. In the cosmic version, the incredibly bright, distant quasar acts as the headlight, and the invisible filaments of the cosmic web are the fog. As the quasar's light journeys for billions of years on its way to Earth, it passes through these vast, tenuous clouds of intergalactic gas. This gas is primarily hydrogen, but it also contains trace amounts of heavier elements like carbon, silicon, and oxygen, left over from generations of long-dead stars. When the light finally arrives at our spectrographs, it tells the story of its long journey. Astronomers spread the light out into a rainbow-like spectrum, looking for specific, sharp dips in intensity at very particular wavelengths. These are absorption lines, and they act like a unique chemical fingerprint. Each dip corresponds to a specific element in one of those invisible clouds that absorbed a tiny fraction of the quasar's light. By identifying these lines and measuring exactly how much they are redshifted, scientists can determine not only the composition of the intervening gas cloud, but also its precise distance from us. A single quasar spectrum is like a core sample drilled through billions of light-years of space, with each absorption line representing a different layer of the cosmic web that the light pierced through. The real power, however, comes from observing many quasars in different parts of the sky. Imagine you have a handful of distant, brilliant lighthouses scattered along a distant, foggy coastline. By studying the pattern of how the fog obscures the light from each lighthouse from your vantage point, you can start to piece together a three-dimensional map of the fog bank itself. Astronomers do the same thing on a cosmic scale. By analyzing the absorption lines in the spectra of thousands of quasars, they can triangulate the positions of these invisible gas clouds. Over time, this painstaking work allows them to reconstruct the architecture of the cosmic web itself, tracing out the vast filaments where galaxies form and the immense, empty voids that separate them. This method provides our only direct way to study the distribution of the majority of the normal matter in the universe, matter that is otherwise completely dark and hidden from our view. Without quasars shining their light from the edge of time, this colossal underlying structure of the cosmos would remain a theoretical guess, a ghostly skeleton we could only infer but never truly observe. And this leads us to a truly profound capability of these distant beacons. Fact 15. The spectra of the most distant quasars act as the ultimate cosmic probes, revealing the chemical composition of the early universe with astonishing clarity. We've already seen how these spectra can map the cosmic web through absorption lines. Now, let's explore what those specific lines actually tell us about the ingredients available when the cosmos was young. A quasar's spectrum is far more than just a measure of distance. It is a detailed chemical census, a forensic report on the elemental makeup of the vast expanses of space that the light has traversed on its billion-year journey. When astronomers analyze these absorption lines, they are looking for the unique signatures of elements heavier than hydrogen and helium, what astronomers call metals. This includes carbon, oxygen, silicon, nitrogen, and even iron. The stunning revelation from the most distant quasars is this. Even when we look back to a time when the universe was less than 1 billion years old, we find clear, undeniable evidence that these heavier elements were already present, mixed into the primordial hydrogen gas. This discovery was and remains a monumental finding. It tells us that the first cycles of star formation, life, and death had already begun and irrevocably transformed the cosmos long before the light from these quasars even started its journey. To understand why this is so significant, we need to rewind to the very beginning. In the immediate aftermath of the Big Bang, the universe was a much simpler place, chemically speaking. The nuclear fusion in the first few minutes produced only the lightest elements, about 75% hydrogen, 25% helium, and a tiny trace amount of lithium. Every other element in the periodic table, the carbon that is the foundation of life, the oxygen we breathe, the iron in our blood, did not exist. These heavier elements had to be forged later in the nuclear furnaces of stars and in the spectacular, violent explosions that marked their deaths. The presence of these metals in the spectra of the earliest quasars provides us with a definitive cosmic clock for this process. It means that the very first generation of stars, often called population 3 stars, must have formed, lived their short, brilliant lives, and exploded as supernova, seeding the surrounding gas with these newly forged elements, all within the first few 100 million years after the Big Bang. These were not gentle, sun-like stars. They were likely colossal giants, hundreds of times more massive than our Sun, burning through their nuclear fuel in just a few million years before dying in cataclysmic hypernova that blasted their newly created elements far out into space. The quasar's light, passing through this newly enriched intergalactic medium, carries the fingerprint of that first epic cycle of cosmic chemistry. We can make this abstract concept more concrete with an everyday analogy. Imagine you walk into a pristine, empty kitchen. A few hours later, you return and find a thin layer of flour dusting the countertops and the faint, sweet scent of vanilla in the air. Even without seeing the baker, you can deduce that someone was there. They were baking, and they used specific ingredients. The absorption lines in a quasar spectrum are that cosmic flour and vanilla scent. The specific ratios of carbon to oxygen, or the presence of silicon, tell a detailed story about the kinds of stars that did the cooking and the types of explosions that mixed the batter. By measuring the exact amounts of these elements at different cosmic epochs, astronomers can trace the history of star formation across the universe, watching as the cosmos grew progressively more enriched with the very materials that would one day form planets and life. The light from these most distant quasars doesn't just show us the universe's ancient structures. It carries the chemical signature of its first creative acts, revealing a cosmos that was already hard at work building the elements for its future complexity. Now, let's explore a phenomenon that transforms the universe into a giant natural telescope. Fact 16. Some quasars are gravitational lenses. This remarkable effect occurs when a truly massive object, like a giant galaxy cluster, positions itself directly in our line of sight to a distant quasar. According to Einstein's theory of general relativity, mass warps the very fabric of spacetime. A colossal amount of mass concentrated in one place, like a galaxy cluster, creates a deep gravitational well that bends the path of light traveling past it. The cluster essentially acts as a colossal, cosmic magnifying glass, distorting and warping the quasar's light in ways that can produce spectacular visual effects. One of the most stunning results of this cosmic lensing is the creation of multiple images of the same single quasar. Instead of seeing one bright point of light, astronomers observe 4 distinct images arranged in a perfect or nearly perfect cross-like pattern around the central lensing galaxy. This beautiful configuration is known as an Einstein cross, named for the physicist whose theory predicted the effect. The first one ever discovered, a quasar known as Q2237+3005, provides a breathtaking example. Here, a single, distant quasar is split into 4 brilliant, blue-hued images, a celestial mirage created by the gravity of a foreground galaxy. It's not an optical illusion in the traditional sense, but a direct confirmation that mass tells spacetime how to curve, and spacetime tells light how to move. The practical value of this lensing goes far beyond creating beautiful astronomical photographs. This natural magnification effect is an incredible gift to science because it amplifies the light of the distant quasar, making it appear much brighter than it actually is. This allows astronomers to study quasars that would otherwise be far too faint and distant to analyze in any detail. It's like having a built-in zoom lens on the universe, giving us a detailed look at the structure of the quasar's accretion disk, its host galaxy, and the surrounding gas clouds with a level of clarity that would be completely impossible without the gravitational assist. By studying these magnified images, we can probe the physics of these distant engines in much finer detail, measuring properties like temperature variations and gas motions within the disk itself. Furthermore, the lensing phenomenon provides a powerful, independent method for weighing the invisible. The exact pattern and separation of the multiple quasar images depend directly on the total mass of the foreground lensing object. This includes not just the visible stars in the galaxies of the cluster, but most importantly, the vast halo of dark matter that surrounds them. By carefully modeling how the quasar's light is bent, astronomers can create a precise map of the lens's gravitational field, effectively allowing them to weigh the dark matter halo and determine its distribution. A single gravitationally lensed quasar, therefore, becomes a dual-purpose tool. It illuminates the details of a distant cosmic powerhouse while simultaneously revealing the hidden architecture of the invisible dark matter that dominates the cosmos. This elegant interplay between light and gravity unlocks secrets across billions of light years, proving that the universe itself provides the tools we need to uncover its grandest mysteries. Now, as we continue to grapple with the sheer scale of these objects, we arrive at a fact that attempts to put their power into a numerical perspective that borders on the incomprehensible. Fact 17. The most powerful quasars can achieve luminosities of over 10 to the 41st watts. Let's try to unpack what that number truly means, because it's so vast it can easily become just another abstract figure. To give it some context, our own sun, which bathes our entire solar system in light and heat, and which drives all weather and life on our planet, has a total energy output of about 3.8 times 10 to the 26 watts. That's a 38 followed by 25 zeros, an enormous number in its own right. Now take that brilliant, life-giving sun and then imagine a trillion of them. A trillion, that's a 1 followed by 12 zeros. A trillion suns all shining together, their combined light and heat fused into a single point-like source. That is the raw, staggering power of a quasar at the peak of its brilliance, with a luminosity of 10 to the 41 watts. We are talking about an energy output so colossal that it defies any earthly analogy. It is the equivalent of detonating a nuclear bomb with the mass of our entire sun every single second. This isn't just a bright object, it is a cosmic furnace of almost mythical proportions, a testament to the ultimate power of gravity. But the truly mind-bending part of this equation is not just the raw number, but the tiny, concentrated region from which all this energy emanates. Remember, this power isn't coming from a sprawling galaxy of a trillion individual stars, each with its own separate engine. This inconceivable energy is being generated from a volume of space not much larger than our own solar system. From a region you could comfortably fit inside the orbit of Pluto, a quasar is unleashing the power of a trillion suns. The concentration of energy is what truly pushes this into the realm of the unimaginable. If you could somehow stand at a safe distance and look at it, the sheer density of power would make the very concept of brightness seem utterly inadequate. It would be a forge of creation and destruction so intense that matter and energy cease to behave in any familiar way. This incredible concentration is what allows quasars to be visible across such epic distances. The light from a trillion suns, if they were spread across 100,000 light-years of space, would diffuse and fade over cosmic distances. But when that same amount of power is focused into a pinpoint, it becomes a laser-like beacon that can punch through the expanding universe for billions of years, arriving at our telescopes still bright enough to be studied in detail. This efficiency and focus is the hallmark of the accretion disk engine, where matter surrendering its gravitational potential energy in the deepest well possible creates the most potent and concentrated light source in the known universe. It is a physical process that takes the fundamental force of gravity and wrings from it every last possible drop of radiant energy, pushing the laws of physics to their absolute limit. This brings us to a fascinating and dynamic aspect of quasars that might seem surprising given their epic billion-year lifetimes. Fact 18. These cosmic giants can blink, with their brightness fluctuating over surprisingly short timescales. We aren't talking about changes over millennia or even centuries, but over periods of mere days, weeks, or months. This isn't a sign of the entire quasar shutting down like we discussed earlier, but rather a rapid flickering, a kind of cosmic heartbeat emanating from its brilliant core. One moment, a quasar might be shining at a certain intensity, and just a few weeks later, it could be noticeably brighter or dimmer. This variability is not a flaw in our observations. It is a vital clue, a fundamental property of quasars that provides one of the most direct ways to measure the physical size of their central engine. The logic behind this is rooted in one of the universe's ultimate speed limits, the speed of light itself. Think about a simple light bulb. If you could magically switch it on all at once, the entire bulb would appear to illuminate instantaneously because it's so small. Now imagine a light source that is 1 light-year across, a gigantic glowing cloud. If you tried to brighten the entire cloud at once, the signal to brighten would have to travel from one end to the other. An observer would see the side nearest them brighten first, and it would take a full year for the brightening signal to reach the far side, and for that side's new light to travel back to the observer. The object cannot appear to vary in brightness faster than the time it takes light to cross its entire diameter. This principle gives astronomers a powerful tool. By measuring how quickly a quasar's brightness changes, they can place a strict upper limit on the size of the region that's actually producing the light. When astronomers applied this logic to the rapid flickering observed in quasars, the results were startling. The fact that a quasar's brightness can change significantly over just a few days tells us that the phenomenally luminous region, the brilliant accretion disk, must be extraordinarily compact. The calculations point to a size of only a few light days across. To put that almost unfathomable scale into perspective, a few light days is still an immense distance. It's roughly the size of our entire solar system out to the orbit of Pluto. But consider what is crammed into that space, an engine that can outshine 1 trillion suns. This incredible concentration of power into such a relatively tiny volume is exactly what we would expect from matter swirling at near light speeds just outside the event horizon of a supermassive black hole. The rapid flickering is the signature of the violent, chaotic storms within that accretion disk, where magnetic flares and instabilities cause local bright spots to flare up and subside, their combined effect making the entire powerhouse seem to pulse from our distant vantage point. This variability does more than just confirm the compact nature of the source. It allows scientists to probe the accretion disk structure in remarkable detail. By observing how the flickering behaves at different wavelengths, for instance, Comparing changes in visible light to changes in ultraviolet or X-ray light, astronomers can actually map the disk. Typically, the shorter wavelength ultraviolet light, which comes from the hotter, innermost part of the disk closer to the black hole, varies more rapidly. The longer wavelength optical light, originating from the cooler, outer regions, tends to flicker on a slightly slower timescale. By carefully tracking these time delays, researchers can effectively measure the physical extent of the disk and even probe the extreme gravitational environment that governs the motion of matter in this ultimate cosmic arena. The blinking of a quasar, a seemingly simple observation, transforms into a sophisticated diagnostic tool, letting us peer into the heart of a gravitational monster and understand the dynamics of its brilliant, chaotic feast. Their incredible reach across space and time makes quasars far more than just distant curiosities. They are active participants in solving one of the greatest mysteries in all of modern science. Fact 19 reveals their profound role in one of the most startling cosmological discoveries of the 20th century. Quasars helped confirm the existence of dark energy. This story begins in the late 1990s, when two independent teams of astronomers were studying a specific kind of stellar explosion known as a Type 1, a supernova. These supernovae are invaluable because they have a known standard brightness, making them perfect standard candles for measuring cosmic distances. To their immense surprise, both teams found that the most distant of these supernovae were significantly dimmer than expected. The only logical conclusion was that they were farther away than our existing models of the universe predicted. This pointed to a universe whose expansion is not slowing down due to gravity, as everyone had assumed, but is instead accelerating, being pushed apart by a mysterious, repulsive force that was dubbed dark energy. This discovery was so revolutionary it won the Nobel Prize in Physics in 2011. But in science, a result of this magnitude requires confirmation from multiple, independent lines of evidence. This is where quasars entered the stage as a powerful, independent witness. Because quasars are visible from such immense distances, they offer a completely different method for mapping the history of the universe's expansion. The technique relies on a specific feature in a quasar's light spectrum. As the quasar's light travels through the cosmic web, it passes through vast clouds of hydrogen gas. These clouds imprint a unique pattern on the spectrum known as the Lyman alpha forest, a dense, forest-like series of absorption lines. The exact distribution and spacing of the lines in this forest are influenced by the large-scale structure of the universe, which itself is shaped by the rate of cosmic expansion over time. To understand how this works, imagine the universe's expansion history as a long, sloping hill. The supernova method gave us a few, very precise measurements at certain points along that hill, like placing flags at specific milestones. The quasar method, using the Lyman alpha forest from hundreds of thousands of quasars, is like painting a continuous line along the entire slope. By analyzing the statistical properties of this forest across a huge number of quasars at different distances, astronomers can trace the expansion rate of the universe over billions of years. When these massive surveys, such as the Sloan Digital Sky Survey's Baryon Oscillation Spectroscopic Survey, or BOSS, applied this technique, their results were unequivocal. They independently confirmed that the expansion of the universe began to accelerate about 5 billion years ago, perfectly aligning with the supernova findings and providing a robust, independent validation of the dark energy effect. The implications of this are staggering. The confirmation of an accelerating universe fundamentally reshaped our standard model of cosmology. We now understand that the cosmos is composed of about 68% dark energy, 27% dark matter, and a mere 5% normal matter. The stars, planets, and everything we see and are made of. Quasars were instrumental in solidifying this tripartite view of the cosmos. Their role highlights a beautiful synergy in modern astronomy, where the most energetic and distant objects in the universe are used to probe the most elusive and dominant component of reality. These ancient beacons, born from the extreme force of gravity, became the very tools we use to discover the repulsive force that now dominates the cosmos's destiny, a force that will ultimately determine the long-term fate of everything. Now, let's shift our gaze from the brilliant, singular beacon at the center and pull back to examine the cosmic neighborhood it calls home. Fact 20 reveals a stunning characteristic of these distant quasars. Their host galaxies are often incredibly dusty and furiously forming new stars. For a long time, the overwhelming glare of the quasar made its host galaxy nearly impossible to see, like trying to spot a firefly next to a massive spotlight. But with the infrared eyes of the James Webb Space Telescope, astronomers are finally pulling back that curtain of light, and what they are finding is a scene of chaotic and prolific creation. These are not serene, stable galaxies. They are cosmic construction sites shrouded in thick clouds of cosmic dust and gas, where stars are being born at a rate that can be hundreds or even thousands of times faster than in our own Milky Way. This creates a fascinating and profound paradox. At the very center of this stellar nursery rages a supermassive black hole, a force of incredible violence and disruption. The conventional wisdom in astronomy suggested that such an energetic engine should be a destructive force, its intense radiation and powerful winds acting like a cosmic hurricane, blowing away the gas clouds that are the very raw material for new stars. It would be like trying to light a candle in the middle of a tornado, yet the observations tell a very different story. There, in the heart of the storm, a phenomenal burst of star formation is taking place. The galaxy is, in essence, building new suns at a breakneck pace right under the nose of a cosmic monster that seems intent on tearing everything apart. So, how can these two extremes, ferocious destruction and frantic creation, coexist? The answer points to a far more complex and nuanced relationship than we first imagined, a delicate dance known as feedback. The quasar's immense energy doesn't just blow material away, it can also trigger the very process of star formation. Imagine a powerful shockwave from the quasar's jets or radiation pressure slamming into a massive cold cloud of gas. This immense compression can actually squeeze the cloud, causing it to collapse under its own gravity and fragment into hundreds of new protostars. In this scenario, the quasar isn't just a destroyer, it's also an agitator, a chaotic midwife that, through its very violence, accelerates the birth of a new generation of stars. This isn't a gentle process, it's a firestorm of creation where the galaxy is forging stars in a frantic, pressurized environment driven by the central engine's fury. This discovery fundamentally challenges our simpler models of galaxy evolution. It suggests that the growth of the central supermassive black hole and the growth of the stellar body of the galaxy are deeply intertwined, happening in tandem during these intense, short-lived phases. The galaxy provides the fuel that feeds the black hole, and the black hole, in turn, through its violent feedback, regulates how and where that fuel gets turned into stars. This intricate balancing act determines the final size and shape of the galaxy. Too much feedback, and the quasar shuts down star formation entirely, leading to a more sedate, elliptical galaxy. The right amount of feedback, however, can ignite a spectacular, if temporary, starburst, shaping a galaxy's future for billions of years. The dusty, star-forming cradles around these ancient quasars are therefore not just a backdrop. They are active participants in a grand cosmic cycle, revealing that the most luminous objects in the universe play a critical and complex role in the very construction of the galaxies they inhabit. And this incredible release of energy doesn't just light up the cosmos, it actively reshapes it, leading us to a truly awesome display of power. Fact 21. These brilliant beacons can launch galaxy-scale winds. We've seen how the raw radiation and relativistic jets can influence their surroundings, but the true regulatory power of a quasar manifests in vast cosmic hurricanes that sweep through the entire host galaxy. These aren't gentle breezes, they are supersonic tempests of ionized gas propelled outward from the central engine at velocities reaching thousands, and in some cases tens of thousands of kilometers per second. These quasar winds represent one of the most significant ways a supermassive black hole communicates its presence to the galaxy it calls home, a dramatic form of feedback that dictates the very life cycle of stars. The mechanism behind these winds is a direct result of the quasar's terrifying luminosity. The intense flood of radiation pouring from the accretion disk carries an immense amount of pressure. When this radiation slams into clouds of gas and dust in the surrounding galactic core, it doesn't just light them up, it physically pushes on them, much like a strong wind pushes against a sail. This radiation pressure can accelerate the gas to phenomenal speeds, launching it out into the galactic halo and beyond. In some of the most powerful quasars, this process is augmented by the intense heat generated by the radiation, which can cause gas to thermally expand and erupt outward in a torrential flow. The result is a colossal outflow that can carry the equivalent of hundreds or even thousands of solar masses of material away from the galactic center every single year. The consequences of this exodus are profound and permanent for the galaxy. The gas and dust being expelled by the quasar wind are the very building blocks for new stars. A galaxy is a star-forming factory, and this expelled material is its raw inventory. By blowing this fuel reservoir clear out of the galaxy, the quasar wind effectively regulates or can even completely shut down the galaxy's ability to create new stars. This solves a long-standing puzzle in astronomy. Why aren't the most massive galaxies in the universe even larger? Our models of cosmic structure formation suggested that these giants should have continued to pull in gas and form stars at a prodigious rate, growing to sizes far beyond what we actually observe. Quasar winds provide the elegant, if violent, solution. The central black hole, in its most active quasar phase, acts as a built-in thermostat. When the galaxy is forming stars too vigorously, it funnels more gas to the center, feeding the black hole and igniting the quasar. The resulting wind then blows the remaining gas away, quenching the starburst and limiting the galaxy's final growth. It's a self-regulating cycle where the galaxy's own central engine decides when it's time to stop building. To visualize the sheer scale of this phenomenon, picture a colossal hurricane, but one that doesn't rage across an ocean for hundreds of miles. It rages across an entire galaxy for tens of thousands of light years. This galactic hurricane doesn't just churn water and air, it churns the fundamental ingredients for future solar systems, scattering them into the desolate voids between galaxies. This isn't a fleeting event either. These winds can persist for millions of years, systematically scouring the galaxy of its star-forming potential. This process, known scientifically as active galactic nucleus feedback, demonstrates that a quasar is far more than a passive light source. It is an active, dominant force in galactic evolution, a central governor that helps set the final mass of its host galaxy and determines its ultimate fate. The brilliance of a quasar, therefore, is not just a spectacle. It is the flash of a cosmic-scale construction project reaching its climax, followed by the powerful winds that signal the cleanup crew has arrived, sweeping away the leftover materials and declaring the main structure complete. Given their mind-bending properties, it seems almost fitting that the name we gave these objects is itself a bit of a puzzle. Fact 22 brings us back to the very beginning. The term quasar is actually a portmanteau, a clever blend of words that perfectly captured the initial confusion surrounding their discovery. The full, original name was quasi-stellar radio source. Let's break that down. Quasi-stellar means star-like, and radio source indicates it was a powerful emitter of radio waves. So astronomers were literally calling them star-like radio sources, a name born from pure observation. They appeared as tiny, unresolved points of light in optical telescopes, just like stars, but their intense radio emission was completely unlike any known star. This contradictory identity was baked right into the name from the very start. This label, however, was just the opening chapter in a story of ongoing classification. As detection methods improved and sky surveys became more comprehensive, astronomers began to find more and more of these brilliant star-like points. There was a catch, though. A significant number of them were strangely silent in the radio part of the spectrum. They had all the same bizarre optical characteristics: the star-like appearance, the high redshift, the incomprehensible luminosity, but they didn't produce the powerful radio waves that had defined the first discovered examples. This created a taxonomic dilemma. Were these radio-quiet objects the same kind of beast as the original quasars, or something different? To account for this growing family, scientists introduced a broader, more inclusive term: quasi-stellar object, or QSO. This new classification encompassed all these incredibly luminous, distant cores, regardless of their radio output. Over time, as our understanding matured, we came to realize that both radio-loud and radio-quiet quasars are fundamentally the same phenomenon: the intensely bright, active nucleus of a distant galaxy, powered by accretion onto a supermassive black hole. The difference in their radio output likely comes down to the specific mechanics of the central engine, particularly whether it is capable of launching those focused, relativistic jets we discussed earlier. A quasar with a powerful jet system tends to be radio loud, while one without, or with a much weaker jet, is radio quiet. It's a bit like the difference between a car with a standard engine and one with a turbocharger. The core principle is the same, but the performance in a specific area is dramatically enhanced. Because of this unified understanding, the original, snappier term quasar has largely won the day in popular usage and even in much of the scientific literature. It has evolved from its specific radio-centric origin to become a powerful catch-all term for these cosmic powerhouses. Today, when an astronomer refers to a quasar, they are generally talking about any galactic nucleus with a luminosity so immense that it drowns out the light of its host galaxy, fueled by a supermassive black hole on a prodigious feeding frenzy. The name quasar is a beautiful artifact of scientific history, a linguistic fossil that preserves the moment of their puzzling discovery, while its modern usage reflects the profound understanding we've built about their true, extraordinary nature as the brilliant hearts of young, evolving galaxies. As we've traveled through the universe of quasars, it's easy to fall into the trap of thinking of them as a single, uniform class of object, brilliant points of light powered by supermassive black holes. But the reality is far more nuanced and fascinating. Our 23rd fact reveals a crucial layer of complexity. Quasars are not all the same. They come in a variety of distinct flavors, and understanding this diversity is key to piecing together the complete picture of how these cosmic engines operate. Just as cars can be sedans, trucks, or sports cars, all designed for different performance and purposes, quasars exhibit a range of characteristics that astronomers have learned to classify, giving us profound insights into their inner workings and our own perspective from Earth. One of the most fundamental divisions in the quasar family is the split between radio-loud and radio-quiet quasars. This distinction harks back to their initial discovery. Radio-loud quasars are the classic powerhouses, emitting tremendous amounts of energy in the radio part of the electromagnetic spectrum. This radio roar is primarily generated by those spectacular, relativistic jets of plasma we discussed earlier, which act like colossal particle accelerators, sending charged particles screaming across intergalactic space. These jets are the unmistakable signature of a particularly energetic and magnetically active central engine. In contrast, radio-quiet quasars, which actually make up the vast majority of all known quasars, are far more subdued in the radio band. Their energy is predominantly released as visible light, ultraviolet radiation, and X-rays from the searingly hot accretion disk itself, without the accompanying powerhouse of focused jets. This tells us that the ability to launch such jets is not a prerequisite for being a quasar. It's a special feature, likely dependent on the specific spin of the black hole and the strength and configuration of the magnetic fields anchored in its accretion disk. But the distinctions don't end there. Astronomers also categorize quasars optically based on the appearance of their spectra into Type 1 and Type 2. This classification has led to one of the most elegant and important ideas in the study of active galaxies, the unified model. The core idea is that the fundamental engine, a supermassive black hole and its accretion disk, is essentially the same in all quasars. What creates the different types we observe is largely a matter of our viewing angle. Imagine a brilliant 100-watt light bulb surrounded by a thick, dusty donut which astronomers call a torus. If we are fortunate enough to be looking directly down the hole of the donut, we have a clear, unobstructed view of the blazing light bulb. This is a Type 1 quasar. From this face-on perspective, we can see the innermost, fastest-moving gas clouds orbiting near the black hole. This high velocity broadens the emission lines in its spectrum, giving them a wide, smeared-out appearance that is the defining hallmark of a Type 1 source. Now, imagine we rotate our viewpoint until we are looking at the system edge-on, staring directly into the side of the thick, dusty donut. Suddenly, our direct view of the brilliant central light bulb is completely blocked. We can no longer see the innermost broad line region. However, we can still see the outer, slower-moving gas clouds that are located above and below the dusty torus. These clouds are illuminated by the hidden central engine, and they produce narrow, sharp emission lines in the spectrum. This is what we classify as a Type 2 quasar. We don't see the dazzling core directly, but we infer its presence from the glow it casts on its surroundings. In many ways, it's like seeing the bright beam of a lighthouse from the side. You know the powerful lamp is there, spinning inside, but your view is obscured by the structure's walls, and you only witness the diffuse light scattering through the fog. This unified model has been spectacularly successful in explaining why we see such a diverse zoo of active galactic nuclei. It suggests that a quasar's appearance is not just about its intrinsic power, but is also a dramatic consequence of geometry and perspective. A faint, narrow-line Type 2 quasar could be the exact same cosmic beast as a brilliant, broad-line Type 1. We're just seeing it from a different angle, a different cosmic seat in the auditorium. This realization was a major leap forward, as it allowed astronomers to simplify a seemingly chaotic menagerie of objects into variations on a single, magnificent theme. The diversity we observe is not a sign of fundamentally different engines, but rather a testament to the complex, structured environment around the black hole and the simple, yet powerful, role that our line of sight plays in shaping what we detect. By studying these different types in unison, we can peer around cosmic corners and understand the complete anatomy of these distant giants, from their fiery hearts to their obscuring, dusty shrouds. Now, let's turn our attention from what quasars are to what they can do for science, because these cosmic giants are far more than just distant spectacles. Fact 24 reveals their profound utility. Quasars serve as unparalleled cosmic laboratories for testing the very laws of physics. Here, in the most extreme gravitational environments in the universe, we can push our understanding of reality to its absolute limits, probing questions that are simply impossible to tackle within the confines of an Earth-bound lab. The region just outside a supermassive black hole's event horizon is a natural testbed for the most radical predictions of Einstein's theory of general relativity. A place where space-time is warped into a knot and matter is subjected to forces beyond comprehension. One of the most striking tests involves the phenomenon of gravitational redshift. Einstein's theory predicts that light struggling to climb out of an intense gravitational field will lose energy, causing its wavelength to stretch and shift toward the red. We see this on a small scale even on Earth, but near a supermassive black hole, the effect is magnified to an extraordinary degree. By carefully analyzing the light emitted by iron atoms whirling at a significant fraction of light speed in the inner accretion disk, astronomers can measure this redshift with incredible precision. The atoms are so deep in the black hole's gravity, that their light is dramatically stretched before it even begins its journey across the universe. These observations perfectly match the predictions of general relativity, providing stunning confirmation that Einstein's century-old theory holds firm even in the most violently distorted regions of spacetime. Beyond testing gravity, quasars offer a unique method for investigating one of the most profound questions in all of physics. Are the fundamental constants of nature truly constant? For decades, physicists have wondered if the numbers that dictate how the universe behaves, like the speed of light or the fine structure constant, which governs the strength of electromagnetic interactions, have remained unchanged since the Big Bang. Quasars provide a direct way to check. Their light, after traveling for billions of years, acts as a tape recording of the laws of physics as they were in the ancient cosmos. When this light passes through clouds of interstellar gas, it absorbs specific wavelengths, creating a unique barcode of absorption lines in its spectrum. The precise spacing of these lines depends intimately on the value of the fine structure constant. Researchers conduct what is essentially a cosmic forensic analysis, comparing the ancient barcode from a distant quasar to the barcode produced by the same elements in laboratories on Earth today. A tiny shift in the spacing would indicate that the fine structure constant was different in the past. Some studies have indeed suggested tantalizing, minuscule variations over billions of years, though the results remain an active and exciting area of debate. The very possibility that we can use these distant beacons to perform such a fundamental test is revolutionary. It means that by observing the universe on the largest scales, we might find clues to a grand unified theory, a set of laws that could explain all forces of nature. Quasars, therefore, are not just subjects of study themselves. They are the most powerful telescopes we have for peering into the very rulebook of the cosmos, allowing us to ask if the laws we take for granted are truly written in stone or if they have evolved along with the universe they govern. This historical rarity brings us to a powerful realization about our own cosmic era. Fact 25: quasars are relatively rare in the modern universe. This statement provides a profound sense of cosmic context, framing the brilliant beacons we've been discussing not as permanent fixtures, but as the brilliant, fleeting fireworks of a bygone age. To truly appreciate the universe we live in today, we must understand that it is a much quieter, more settled place than it was in its wild youth. The era of brilliant quasars was a specific, violent chapter in cosmic history, one that most large galaxies have now passed through, leaving behind the dormant, dark hearts we find at the centers of galaxies like our own Milky Way. The Golden Age of Quasars, a period astronomers often refer to as cosmic noon, occurred roughly 10 billion years ago. This was not the very dawn of time, but a later, incredibly fertile period when the universe was about a third of its current age. During this epoch, the cosmos was a bustling, chaotic construction site. Galaxies were closer together, frequently colliding and merging, and they were rich with vast, turbulent reservoirs of cold gas and dust. This abundance of fuel was the key ingredient. It provided the perfect conditions for supermassive black holes to embark on spectacular feeding frenzies, igniting quasars all across the sky. If you could have looked up at the night sky 10 billion years ago, it would have been dotted with these brilliant points of light, each one a testament to a galaxy in the throes of a violent growth spurt. So what changed? Why is our current universe so much more sedate? The primary reason is a simple, universal law: the fuel supply eventually runs out. Just as a roaring fire dies down when it exhausts its wood, a quasar's brilliance fades as it consumes the dense gas clouds in its immediate vicinity. Over billions of years, this fuel has been used up in two major ways. First, a significant portion was directly consumed by the black holes themselves during their active quasar phases. Second, and perhaps more importantly, much of the remaining gas was either forged into stars or blown clean out of the galaxy by the very quasars it was feeding, through those powerful winds and jets we discussed earlier. Once a galaxy's central black hole has consumed or cleared out its nearby fuel reserves, the dazzling accretion disk simply cannot be sustained. The brilliant engine sputters and goes quiet, transitioning from a raging quasar to a dormant supermassive black hole. Furthermore, the environment of the universe itself has evolved to become less hospitable for such frenetic activity. As the cosmos has continued to expand, galaxies have grown farther apart. Major galaxy mergers, which were common in the crowded early universe and were fantastic at funneling fresh gas toward the center to ignite a quasar, are now much rarer events. In our modern, more spacious universe, most massive galaxies have achieved a state of relative stability. Their gas is often locked up in long-lived stars or exists in a hotter, more diffuse form that is less prone to collapsing directly into the central black hole. The chaotic, fuel-rich conditions that were the norm during cosmic noon have largely been replaced by a more orderly and, frankly, more fuel-efficient cosmic economy. This transition has a direct and personal connection for us. The supermassive black hole at the center of our Milky Way, Sagittarius A star, is a perfect example of this cosmic retirement. With a mass of over 4 million suns, it certainly has the potential to become a quasar, but it sits quietly, emitting only a faint whisper of radiation because it simply doesn't have enough gas to consume at a rate that would ignite its engine. Our galaxy, along with most other massive galaxies we see nearby, has matured out of its chaotic, brilliant adolescence. The age of quasars was a spectacular but finite phase in cosmic evolution. Their scarcity today is not a sign of a dying universe, but rather a sign of a maturing one, a cosmos that has moved from the explosive construction of its largest structures to a longer, more stable era where life can slowly and quietly emerge on planets around peaceful stars like our own. This discovery, arriving in the 1960s, didn't just add a new class of object to our celestial catalogues. It fundamentally rewrote the rules of the game, forcing a profound paradigm shift in our understanding of the cosmos. Before quasars, the universe, while vast, was perceived as a relatively calm and predictable place. Stars shone steadily, galaxies rotated majestically, and the most dramatic events were thought to be supernova explosions within galaxies. The realization that a single star-like point could be billions of light-years away, yet outshine a trillion suns, shattered that serene picture. It introduced a universe of unimaginable violence and energy where processes dwarfing stellar fusion were at work. Astronomers were suddenly confronted with a cosmos capable of concentrating more power into a volume smaller than our solar system, than an entire galaxy of stars, a concept that was both baffling and revolutionary. One of the most immediate and profound impacts was on the acceptance of supermassive black holes. Before quasars, the idea of million or billion solar mass black holes was a fringe theoretical concept viewed by many with deep skepticism. They seemed like mathematical oddities, too extreme to actually exist in nature. Quasars provided the first, and ultimately the most compelling, evidence that these gravitational monsters were not only real but relatively common. The only conceivable engine that could explain the staggering energy output, its origin in such a tiny region, and its rapid variability was the gravitational collapse of matter onto a supermassive black hole. The quasar model turned a speculative idea into a cornerstone of modern astrophysics, establishing that these dark giants reside at the heart of most large galaxies and play a critical role in their evolution. Furthermore, quasars delivered undeniable proof of an expanding universe on a truly grand scale. While Hubble's work with galaxies had demonstrated the expansion locally, the extreme redshifts of quasars showed that this was a universal phenomenon affecting objects at the farthest reaches of observable space. The fact that we could see these brilliant beacons from such immense distances confirmed that the universe was not only expanding, but that we could use this expansion as a tool to map cosmic history. The redshift-distance relation became the fundamental yardstick for cosmology, and quasars, with their high luminosities, became the perfect mile markers, allowing us to probe deeper into the cosmos than ever before. They transformed the redshift from a curious spectral effect into the key tool for measuring the size, age, and fate of the universe. This new, violent universe also forced a complete rethink of galactic evolution and the nature of galactic cores. Prior to the 1960s, the centers of galaxies were thought to be relatively peaceful places, perhaps densely packed with stars, but not inherently dynamic. Quasars revealed that the core of a galaxy could be the site of the most energetic and dominant process in its entire life cycle. This introduced the concept of the active galactic nucleus, or AN, as a distinct and crucial phase of a galaxy's development. It became clear that galaxies were not static islands but dynamic systems that underwent violent growth spurts, and that the engine driving this transformation was the supermassive black hole at its center. This connected the growth of the black hole to the growth of the galaxy itself in a feedback loop, a concept that is now central to all models of how galaxies form and evolve. The quiet galaxy we see today, like our Milky Way, was now understood to have likely hosted a brilliant, violent quasar in its past, forever changing our perspective on our own cosmic home. Now, let's explore a technique that's almost like cosmic time travel, allowing astronomers to uncover a quasar's history long after its central engine has fallen silent. Fact 27. The light from these brilliant beacons can create echoes that reveal their past activity. We've discussed how the light from the most distant quasars takes billions of years to reach us, showing us the object's ancient state. But there's another, more local kind of time machine at work, one that operates on timescales of mere centuries or millennia, using the very dust that floats in the quasar's own galactic neighborhood. The principle works like this. Imagine a quasar at the center of its galaxy, blazing with intense ultraviolet and X-ray radiation. This light streams outward in all directions at, of course, the speed of light. Some of this light travels directly toward us, giving us the brilliant point source we see, but a significant portion of it floods out into the galaxy, illuminating vast, complex clouds of cosmic dust that swirl around the central region. This dust is not like household dust. It's made of tiny, solid particles of carbon and silicate, similar to fine soot or sand. When the high-energy photons from the quasar slam into these dust grains, they don't just bounce off. The dust absorbs the energetic light, heats up considerably, and then, after a short delay, re-radiates that energy as longer wavelength infrared light. This time delay is the key to the entire phenomenon. The light traveling directly from the quasar to us gives us a real-time view, or rather, a view as it was billions of years ago. However, the light that takes a detour, first traveling from the quasar to a distant dust cloud and then being re-emitted toward us, arrives later. The path is longer, creating a literal echo. It's analogous to sound echoing in a vast canyon. If you shout, the sound travels directly to a listener, but it also travels to a far canyon wall, bounces off, and then arrives at the listener's ears a moment later. That delayed sound is an echo of your original shout. In the cosmic version, the brilliant flash of the quasar is the shout, and the infrared light from the heated dust is the echo that reaches our telescopes sometimes thousands of years after the direct light has passed us by. What makes this so valuable for science is that it allows astronomers to effectively look into the quasar's recent past without having a time machine. Let's say we observe a quasar that currently appears to be in a relatively quiet, dim state. By training powerful infrared telescopes like the James Webb Space Telescope on it, we might detect a brilliant, glowing shell of warm dust surrounding it. The infrared light from that shell is a light echo. By analyzing its properties and calculating the distance the light had to travel to reach the dust and then come to us, we can determine that this echo was caused by a tremendous flare of activity that occurred in the quasar's core, for example, 500 years ago. That brilliant flash has long since faded from view in direct light, but its echo is still arriving, telling us a story of a violent outburst that we would have otherwise completely missed. This technique can reveal the detailed history of a quasar's activity cycles. By mapping different shells of dust at various distances from the central engine, astronomers can piece together a timeline of outbursts, much like reading the rings of a tree. A dust cloud 100 light-years away might be glowing with an echo from a flare that happened 100 years ago, while a cloud 500 light-years away might show the signature of an even more powerful event from 500 years in the past. This data reveals that quasars are not steady, unwavering candles. They have active and quiet periods, likely corresponding to when large clumps of matter, like giant gas clouds or even entire stars, plummet into the accretion disk, causing a temporary but dramatic brightening. These light echoes provide the historical records of these feasts, allowing us to understand the diet and behavior of these cosmic giants over timescales that are far too long for any single human lifetime to observe directly. It's a beautiful and clever way of using the universe's own architecture to preserve a history that would otherwise be lost to time, turning silent clouds of dust into glowing archives of past cosmic violence. This hunt for cosmic couples brings us to a fascinating and cutting-edge frontier in astrophysics. Fact 28 reveals that these brilliant beacons can help us find supermassive black hole binaries. We've already explored how the violent process of galaxy formation often involves collisions and mergers. When two large galaxies slam together, theory strongly suggests that their central supermassive black holes should eventually encounter one another, forming a bound pair locked in a gravitational dance at the very heart of the newly combined galaxy. The challenge has always been proving that these predicted binary pairs actually exist. Because black holes themselves are dark, detecting them directly is incredibly difficult unless they are actively feeding and shining as quasars. This is where the unique, fluctuating light of a quasar becomes an essential tool for this cosmic detective work. The telltale sign of a potential binary system is a specific periodic flicker in the quasar's brightness. Imagine watching a brilliant lighthouse whose beam seems to pulse with a strange clockwork regularity, not the rapid, chaotic flickering from instabilities in a single disk, but a smooth, repeating pattern over a timescale of years or even decades. This kind of predictable variation could be the signature of two black holes, not one, orbiting a common center of mass. As this colossal pair swings through its orbit, its gravitational influence can periodically disturb and modulate the flow of gas in the surrounding accretion disk. Think of it as a cosmic-scale version of the tides on Earth, which are caused by the gravitational pull of the Moon and Sun. In a binary black hole system, the orbit of the two giants can create a rhythmic pattern in the way fuel funnels onto one or both of the black holes, causing the overall light output of the quasar to rise and fall in a predictable, repeating cycle that astronomers can detect over years of careful observation. One of the most compelling candidate systems discovered to date is a quasar known as OJ287. For decades, astronomers have monitored its light, and the data reveals a remarkably regular pattern of outbursts approximately every 12 years. This periodicity is a strong hint that the brilliant activity we see is not driven by a single, solitary monster, but by a pair of supermassive black holes locked in a close orbital embrace. Another famous candidate is PG 1302-102, which shows a period of about 5 years. In these systems, the orbit itself acts as a cosmic metronome, ticking off the years as the two black holes circle one another, their immense gravity governing the tempo of the entire accretion process and leaving its rhythmic imprint on the light that travels across the universe to our telescopes. The implications of confirming such systems extend far beyond simply proving a theoretical prediction. Finding a binary supermassive black hole is a crucial stepping stone toward one of the most anticipated events in all of astronomy, the detection of low-frequency gravitational waves. Gravitational waves are ripples in the fabric of spacetime itself, first predicted by Einstein and directly detected for the first time in 2015 from the merger of stellar mass black holes. Supermassive black hole binaries, however, generate waves with a much lower frequency and a much longer wavelength. These waves are not detectable with Earth-based instruments like LIGO. Instead, they require a space-based observatory. This is the mission of projects like the Laser Interferometer Space Antenna, or LISA, a planned fleet of 3 spacecraft that will form a gravitational wave observatory in solar orbit. As a binary pair of supermassive black hole spirals inward over millions of years, they stir the spacetime around them into a continuous, undulating ripple. This creates a constant, low hum of gravitational waves that permeates the entire galaxy and eventually the cosmos. This is not the violent, final chirp of a merger, but a persistent background drone like the deep, resonant note of a cello that plays on and on. By carefully studying the periodic light variations from quasars, astronomers can identify the best possible targets for LISA to observe. They can essentially point future instruments toward the parts of the sky where this cosmic hum should be the loudest. Detecting these waves would open an entirely new window on the universe, allowing us to listen to the symphony of spacetime itself and providing direct, dynamical evidence for the hierarchical model of galaxy formation through mergers. Every candidate binary quasar we find is not just a curiosity. It is a potential landmark in this future map of the gravitational universe, a signpost pointing toward the deepest, most fundamental vibrations of reality. Now, let's turn our focus from the grand, cosmic scale impacts of quasars to the turbulent heart of the engine itself. Fact 29. The brilliant accretion disks that power these beacons are not always stable. We often picture this whirlpool of matter as a smooth, orderly flow, like water spiraling down a drain, but the reality is far more chaotic and explosive. The flow of material onto a supermassive black hole is a constant battle between immense gravitational forces and other physical pressures, a battle that can lead to dramatic and violent instabilities. These aren't minor fluctuations, they are episodes where the entire system seems to lurch, dumping vast, sudden quantities of matter onto the black hole in a furious binge that can cause the quasar's brightness to surge in spectacular outbursts. To understand why this happens, we need to think about the accretion disk not as a simple fluid, but as a complex structure governed by competing forces. One of the most critical instabilities is known as the thermal viscous instability. In a stable disk, the rate at which gas spirals inward is balanced by the efficiency with which the disk radiates away the heat generated by friction. But this balance is precarious. Imagine trying to cook on a stove where the burner's heat keeps changing. If a certain region of the disk heats up slightly, its viscosity, its internal stickiness can increase. This allows the material in that region to lose orbital energy more efficiently, causing it to spiral inward faster. But as it moves inward, it compresses and heats up even more, releasing a torrent of radiation. This can create a runaway feedback loop. More heat leads to lower viscosity, which leads to faster inflow, which leads to even more heat. The result is a wave of heating and rapid accretion that propagates through the disk like a tidal wave, dramatically increasing the amount of fuel being fed to the black hole in a short, furious burst. We can visualize this with a more earthly analogy. Think of a congested highway during a sudden, heavy downpour. Under normal conditions, traffic flows at a steady, if slow, pace. But the rain, representing a thermal instability, changes the friction of the road. This causes some cars to slow down abruptly while others try to swerve, creating a chain reaction that leads to a massive traffic jam. Then, when the rain stops and the road begins to dry, the jam suddenly clears and a huge wave of cars all accelerates forward at once, flooding the next exit ramp. In the accretion disk, the traffic jam is a buildup of material in the cooler, outer regions. When the instability is triggered, this built-up reservoir of gas is suddenly released, rushing inward all at once and creating a brilliant flash as it plummets toward the event horizon. The observational signature of this is a dramatic and sometimes predictable flare in the quasar's brightness across multiple wavelengths. Astronomers monitoring these objects over years sometimes see their luminosity double or even increase tenfold over a period of weeks or months before gradually settling back down. These are not the brief, day-to-day flickers caused by small magnetic flares, but major, system-wide events that signify a fundamental rearrangement of the disk structure. By carefully studying the rise and fall times of these outbursts, scientists can actually probe the physical conditions within the disk itself, measuring properties like its density and temperature profile that would be otherwise impossible to discern from 13 billion light-years away. But the instabilities don't stop there. Another fascinating source of turbulence comes from the interplay between the disk and the black hole's own spin. If the black hole is rotating rapidly, it can drag the very fabric of space-time around with it, an effect known as frame dragging. This can warp the inner part of the accretion disk, twisting it out of its flat plane and causing it to precess or wobble like a spinning top. This precession can itself be unstable, leading to situations where different warped rings of the disk periodically align and crash into each other, triggering violent surges in accretion. Furthermore, the powerful magnetic fields threading the disk can become tangled and stressed to a breaking point, then suddenly snap and reconnect in colossal magnetic storms. These events can catapult vast clouds of charged particles clear out of the disk, both feeding the black hole in a sudden gulp and powering the immense jets that blast outward from the poles. Studying these violent tantrums is about more than just understanding why a quasar flickers. It provides a unique laboratory for exploring the behavior of plasma and magnetized fluids under the most extreme gravitational conditions possible. The physics that governs an accretion disk around a black hole is the same physics that describes the formation of stars and planets from protoplanetary disks, just scaled up to an almost unimaginable level of energy. By observing how these cosmic engines stutter and surge, we are learning the fundamental rules that dictate how matter behaves when it is pushed to its absolute limits, teaching us about the dynamics that fuel the most powerful and persistent sources of light in the known universe. But to truly grasp the anatomy of these cosmic giants, we need to look at them in a different kind of light, or rather, in all kinds of light. Fact 30. Quasars emit across the entire electromagnetic spectrum. The brilliant point we see with our eyes or with optical telescopes is just one small slice of their total energy output. These objects are cosmic radio stations, brilliant ultraviolet beacons, searing X-ray furnaces, and even sources of the most energetic gamma rays all rolled into one. Each band of this spectrum acts like a different instrument in a grand cosmic orchestra, and by listening to all of them at once, we can decipher the complex music of the quasar's inner workings, understanding the roles played by its different components. This symphony of light originates from distinct physical processes happening in different regions of the quasar system. Starting at the low energy end, the powerful radio waves we detect almost always come from those colossal relativistic jets. As charged particles are whipped along the intense magnetic fields within these jets, they spiral at near light speeds, a process known as synchrotron radiation that generates a characteristic radio roar. Moving up in energy, the dazzling visible and ultraviolet light that makes quasars so brilliant to our eyes is the direct thermal radiation from the accretion disk itself. This is the superheated plasma, glowing white-hot as it spirals inward, with the innermost, hottest parts radiating most of their energy in the ultraviolet. Then we have the infrared emission, which often reveals the hidden structure of the quasar. This warm, longer wavelength light is largely produced by the vast, obscuring torus of dust that surrounds the central engine. The dust absorbs the intense ultraviolet and optical light from the accretion disk, heats up to hundreds of degrees, and re-radiates the energy as a pervasive infrared glow, effectively outlining the shape of this cosmic donut. The high-energy end of the spectrum reveals the most violent and extreme processes. The intense X-rays that stream from quasars are thought to be generated in a mysterious region called the corona, a tenuous, superheated plasma of electrons hovering just above the accretion disk. This is analogous to the Sun's corona, but unimaginably hotter and more energetic. In a process known as inverse Compton scattering, photons from the hot accretion disk collide with these ultra-energetic electrons in the corona, receiving a massive energy boost that transforms them from ultraviolet photons into powerful X-rays. Finally, at the very highest energies, we have gamma rays. These are typically produced in the most powerful, radio-loud quasars, where particles within the jets are accelerated to such fantastic speeds that their collisions with photons or other particles generate this ultimate form of electromagnetic radiation. Each wavelength, from the long, low notes of radio to the piercing shriek of gamma rays, tells a different part of the story. This multi-wavelength approach transforms our understanding from a flat picture into a rich, three-dimensional model. It's the difference between looking at a photograph of a car and being a mechanic who can listen to the engine, feel the heat from the exhaust, and see the glow of the brake discs. An optical telescope like Hubble might show us the brilliant visible light of the accretion disk. The Chandra X-ray Observatory then reveals the searing corona and the high-energy processes at the base of the jets. The Spitzer and James Webb Space Telescopes map the warm dust in the infrared, delineating the torus, and ground-based radio telescopes like the Very Large Array trace the immense, far-reaching structure of the jets and lobes. Only by combining all these observations can we assemble a complete portrait of the quasar, understanding how the calm, orderly inflow of the disk connects to the chaotic violence of the corona and the focused, relativistic fury of the jets. This holistic view is absolutely essential because without it, we would be like the proverbial blind men touching an elephant, each describing a different part but missing the magnificent, terrifying, and interconnected whole. Indeed, we keep returning to this central, beautiful puzzle because it strikes at the very heart of our understanding of cosmic genesis. The existence of billion solar, mass black holes in a universe that was only a few 100 million years old is not just a curious anomaly. It is a fundamental challenge that forces us to re-examine the physics of the universe's first moments. Our standard models of black hole growth have a clear, logical progression. A massive star collapses, forming a black hole seed of a few dozen solar masses, and then this seed gradually grows over billions of years by steadily accreting gas and merging with other black holes. But the earliest quasars are like finding a fully grown, 50-foot-tall toddler. The timeline simply doesn't add up. For these objects to achieve such staggering masses so quickly, they must have either started from colossal seeds, bypassing the stellar collapse stage entirely, or they must have fed at a rate so ferociously efficient it pushes against the very limits dictated by physics. Let's explore the first compelling pathway, the concept of direct collapse black holes. This theory suggests that in the dense, pristine environment of the early universe, the first structures weren't individual stars but vast, massive clouds of pure hydrogen and helium. Without heavier elements to help them cool and fragment efficiently, these clouds could have collapsed directly under their own immense gravity, skipping the star-forming stage altogether. The result wouldn't be a mere stellar remnant, but a gargantuan seed black hole born with a mass of 10,000, 100,000, or even 1,000,000 times that of our Sun. This is the ultimate head start. With a seed of this magnitude, the subsequent growth to 1 billion solar masses becomes a much more tractable problem, even within the tight constraints of the early cosmic calendar. It's the difference between trying to build a skyscraper by first making a single brick versus having a prefabricated 10-story core already in place. The other, equally radical possibility is that the first black holes, even if they started from more conventional stellar seeds, experienced a period of absolutely breakneck growth, feasting on the surrounding gas at a rate we would consider unsustainable. This involves a concept known as super-Eddington accretion. The Eddington limit is a theoretical ceiling that describes the maximum rate at which a black hole can pull in matter before the intense radiation pressure from its own accretion disk pushes back and blows away the surrounding fuel supply, effectively turning off the tap. It's like a fire that burns so hot it creates its own windstorm, scattering the very wood it needs to keep burning. However, theorists propose that in the unique conditions of the early universe, with vast, dense, and chaotic reservoirs of gas, black holes might have been able to briefly exceed this limit. Matter could have been funneled inward in dense, lumpy streams or through a radiatively inefficient flow where the energy produced isn't effectively converted into outward radiation pressure, allowing the black hole to gorge itself in a frantic, short-lived binge. This isn't merely an abstract debate, it has profound implications for the entire narrative of cosmic dawn. If direct collapse was the primary method, it means the first black holes were fundamental building blocks of the cosmos, appearing almost simultaneously with the very first stars and galaxies, their immense gravity immediately beginning to sculpt their surroundings. If, on the other hand, super-Eddington accretion was the key, it paints a picture of a violently competitive early universe where the first black holes that could momentarily break the rules won the cosmic lottery, ballooning in size to become the dominant quasars we observe. The reality might be a complex combination of both, with direct collapse providing the most promising seeds and periods of hyper-efficient feeding allowing them to capitalize on their initial advantage. The light from these most distant quasars is the only hard evidence we have from this formative epoch, and its message is clear. Our standard, gradualist models of cosmic structure formation are incomplete. The infancy of the universe was a time of radical and rapid construction, where the rules were different and the pace was almost unimaginably frantic. This brings us to a fascinating and sophisticated application of these distant giants, one that turns their complex nature into a tool for measuring the cosmos itself. Fact 32 reveals that quasars can be used as standard candles. Now, the term standard candle is one of the most important concepts in all of astronomy. It refers to any celestial object whose intrinsic brightness, the amount of light it actually emits, is known. Why is that so crucial? Because if you know how bright something truly is, and you measure how dim it appears from Earth, you can calculate its distance with remarkable precision. It's like knowing the exact wattage of a light bulb. If you see it shining brightly, you know it's close, but if it appears as a faint speck, you can deduce it must be very far away. For decades, the gold standard for this has been a specific type of stellar explosion called a Type 1, a supernova. These supernovae have a very consistent peak brightness, making them fantastic cosmic mile markers. Quasars, with their wild and unpredictable flickering, seem like the absolute worst candidates for this job. Their luminosity can vary by enormous factors over short periods, and no two quasars have exactly the same peak power. They are the chaotic, unruly teenagers of the cosmos compared to the reliable, predictable supernova. So, how could they possibly serve as standard candles? The answer lies not in their total brightness, but in a specific, subtle relationship discovered deep within their structure. Astronomers have found that there is a remarkably tight correlation between the overall luminosity of a quasar and the physical size of a specific region near its center called the broad line region. This is the zone of hot, fast-moving gas clouds that orbit very close to the supermassive black hole, and their high velocity is what produces the broad, smeared-out emission lines in the quasar spectrum. This connection makes intuitive sense if you think about it. A brighter quasar has a more powerful accretion disk engine. That more intense radiation field pushes outward with greater force, and it can ionize gas that is farther away from the central black hole. Therefore, a more luminous quasar will have a larger broad line region, while a dimmer one will have a more compact one. This radius-luminosity relation is the key that unlocks the quasar's potential as a distance measuring tool. Here's how it works in practice. By carefully analyzing the spectrum of a quasar, astronomers can actually measure the size of its broad line region. They do this using a clever technique called reverberation mapping, which observes the time delay between a flare in the accretion disk's brightness and the subsequent response in the broad emission lines. This delay is literally the time it takes for light to travel from the central engine out to the broad line region gas, giving a direct measurement of the region's physical size. Once you know the size, the radius-luminosity relation tells you the quasar's true, intrinsic luminosity. You now have your standard candle. By comparing this known intrinsic brightness to the apparent brightness we measure from Earth, astronomers can calculate the quasar's distance. This method provides a completely independent way to measure cosmic distances, separate from the traditional supernova technique. In science, having multiple, independent methods to measure the same thing is absolutely invaluable. It's the ultimate cross-check. If the distances derived from supernova and the distances derived from quasars agree, it gives us tremendous confidence that our understanding of the cosmic distance ladder is on solid ground. Any discrepancy, however, would be a major clue that we might be missing something fundamental about the physics of these objects or the nature of cosmic expansion itself. The development of this technique is a testament to scientific ingenuity, turning a weakness, the variability of quasars, into the very tool that allows us to probe their structure and use them as cosmic beacons. It's not a perfect method. There is some scatter in the relationship, and it requires painstaking observations. But for the most distant quasars where other standard candles are too faint to see, this approach offers a promising path forward. As we collect data on more and more quasars, this radius-luminosity relation is becoming more refined and reliable, adding another powerful instrument to our cosmic toolkit. It demonstrates that even the most chaotic and energetic phenomena in the universe can be understood and harnessed, their hidden regularities uncovered to help us map the vast, expanding expanse of space and time. Shifting our focus to the light itself, we encounter a fascinating and revealing spectral signature that acts like a cosmic weather report for the hurricane-force winds blasting from a quasar's core. Fact 33. Some quasars exhibit what are known as broad absorption lines, a specific and powerful feature seen in their spectra. To understand what these are, let's first recall that a quasar's spectrum is normally dominated by bright, broad emission lines, the fingerprint of hot, fast-moving gas clouds orbiting the central black hole. In a broad absorption line quasar, however, astronomers see something very different superimposed on that familiar pattern. Deep, wide troughs that appear to be gouged out of the spectrum, like someone took a cosmic chisel and carved away huge chunks of the quasar's light. These aren't mere dips, they are vast, dark valleys in the rainbow of the quasar's light. The origin of these dramatic features lies not in anything being emitted, but in something being absorbed. These troughs are created by incredibly dense, fast-moving winds of gas that are flowing directly outward from the quasar's core, and this is the crucial part. They are moving along our direct line of sight to the brilliant accretion disk. Imagine you're standing in front of a brilliant lighthouse, but between you and the beacon is a massive, fast-moving storm cloud of superheated gas and dust. The light from the lighthouse has to pass through this cloud, and the cloud absorbs specific wavelengths of that light, creating a dark shadow in the spectrum you observe. In the case of a Baal quasar, this storm cloud is a galactic scale wind, and the absorption is so complete and covers such a wide range of velocities that it creates those characteristic broad, deep troughs instead of thin, sharp lines. The fact that these absorption lines are blue shifted is the final, critical clue that tells us the story of this wind's motion. As we've learned, when an object moves toward us, its light is compressed, shifting its wavelength toward the blue end of the spectrum. The broad absorption troughs in these quasars are distinctly blue shifted, which means the material causing the absorption is hurtling toward us at phenomenal speeds. We are essentially looking directly down the barrel of a cosmic blowtorch. These outflows aren't just gentle breezes, they are gales of ionized gas racing away from the central engine at velocities that can reach 20% of the speed of light or more. That's fast enough to travel from the Earth to the Sun in under an hour. This single observation transforms the spectrum from a simple identifier into a dynamic map of motion, revealing the raw power of the quasar to eject its own fuel supply across the galaxy. For astronomers, discovering a BL quasar is like striking scientific gold. These objects provide a direct and unparalleled laboratory for studying the mechanics of quasar feedback, the very process that allows a central black hole to regulate the growth of its host galaxy. By meticulously analyzing the shape, depth, and width of these broad absorption troughs, researchers can deduce an astonishing amount of information about the wind itself. The width of the trough reveals the range of velocities present within the outflow, from the fastest moving material at the leading edge to slower streams trailing behind. The depth of the trough indicates the density of the gas. Deeper troughs mean thicker, more opaque winds that can block more of the quasar's light. Perhaps most importantly, by identifying the specific chemical elements responsible for the absorption, such as carbon, silicon, and nitrogen, scientists can determine the wind's chemical composition, which tells us what the quasar is actually blowing out into intergalactic space. This data is vital for solving one of the great puzzles of galaxy evolution. How can a process as violent as a quasar wind, which seems purely destructive, also be a creative force? The answer may lie in the detailed properties of these BL outflows. A powerful, fast-moving wind can indeed strip a galaxy of its star-forming gas, quenching future stellar birth. However, if the wind is slightly slower and denser, it might not escape the galaxy entirely. Instead, it could sweep up surrounding gas like a cosmic snowplow, compressing it into dense shells on the galactic outskirts. This very compression can then trigger the collapse of those gas clouds, igniting a wave of new star formation in a ring around the galaxy's center. The broad absorption lines allow us to measure the exact blast setting of the quasar's engine, helping us understand whether a specific quasar is in a destructive phase, blowing its galaxy clean, or in a more constructive phase, sculpting and stimulating its growth from within. These cosmic signatures are therefore not just curiosities. They are the key diagnostics that show us how the most energetic objects in the universe act as master architects, using their own violent breath to shape the evolution of the galaxies they call home. It turns out that location is just as important for quasars as it is for real estate, even on a cosmic scale. Our 34th fact reveals a stunning pattern about their neighborhoods. The most luminous quasars in the early universe often made their homes in incredibly crowded environments. When astronomers map the skies around these ancient beacons, they find them not in lonely, isolated voids, but in the densest, most bustling metropolitan areas of the young cosmos. These regions were the burgeoning hubs of activity, the direct precursors to the most massive galaxy clusters we see in the universe today, collections of hundreds or even thousands of galaxies bound together by gravity. This isn't a mere coincidence, it's a fundamental clue about the very conditions needed to ignite and sustain such a brilliant cosmic engine. Think of it like trying to light a colossal bonfire. If you're in the middle of a vast, empty desert, you might struggle to find enough wood to get a significant flame going, and even if you do, it will burn out quickly. But if you are in the heart of a dense forest, fuel is abundant everywhere you look. For a supermassive black hole, the wood is the cold gas and dust that fills a galaxy. In a rich, crowded environment, this raw material is simply more plentiful. A galaxy swimming in a dense sea of intergalactic hydrogen has a nearly limitless reservoir to draw from, either by slowly accreting it or, more dramatically, by stealing it from its neighbors during close encounters. This constant, ample supply of fuel is the first and most critical ingredient for powering a long-lasting, brilliant quasar. But the crowding does more than just provide a steady gas supply. It actively creates the triggers for a quasar's explosive activity. In these dense protoclusters, galaxies lived much closer together than they do in today's more spread-out universe. This proximity made gravitational interactions, close passes, and full-blown mergers between galaxies a common, almost routine event. A galaxy merger is the ultimate catalyst for a quasar. When two large galaxies slam together, their intricate gravitational dance creates chaos. Vast streams of gas that were once peacefully orbiting in the outer regions of the galaxies are violently shaken loose and funneled directly toward the newly combined galactic center. This is like throwing a truckload of logs onto a smoldering fire all at once. The sudden, massive infusion of fresh fuel onto the central black hole ignites a spectacular burst of accretion, turning a quiet nucleus into a brilliant quasar that can blaze for millions of years. The crowded environment, therefore, doesn't just sustain the quasar. It provides the specific, violent events that are often required to turn it on in the first place. We can see a fascinating local echo of this process in our own cosmic backyard. The brightest active galactic nucleus relatively near to us is found in the galaxy Markarian 2311, which is actually the result of a spectacular collision between two galaxies. This merger has triggered a tremendous burst of star formation and is also feeding its central black hole, creating a brilliant, though not quite quasar-level, beacon. This provides a nearby, observable example of the same physics that was likely responsible for the most powerful quasars in the early universe. The key difference is one of scale and frequency. In the dense environments of the cosmic dawn, these galaxy-altering interactions were the norm, not the exception, creating the perfect cosmic petri dish for the most extreme and luminous objects in the universe to flourish. This remarkable power to reshape their surroundings leads us to a profound capability of these cosmic giants. Fact 35. Quasars can generate their own form of cosmic-scale light pollution. We often think of light pollution as a human problem, the glow from our cities that washes out the faint stars in the night sky. But on a far grander and more fundamental level, a quasar creates a similar effect, not by obscuring our view, but by fundamentally altering the very state of matter across millions of light years. The mechanism behind this is known as ionization, and it involves the most energetic part of the quasar's brilliant output. To understand ionization, picture a simple hydrogen atom, the most basic and common building block of the universe. It consists of a single proton as its nucleus with a single electron orbiting around it. Neutral hydrogen gas is simply a vast collection of these intact atoms, and it has a particular property. It's opaque to certain kinds of ultraviolet light. This is why the early universe was shrouded in a thick fog. The space between galaxies was filled with this neutral hydrogen, blocking the light from the first stars and galaxies. Now, imagine a torrent of high-energy ultraviolet photons, the kind that pours relentlessly from a quasar's accretion disk. When one of these energetic photons smashes into a neutral hydrogen atom, it acts like a cosmic hammer, delivering so much energy that it knocks the electron clean off the proton. The atom is no longer neutral. It has been split into a free-floating, positively charged proton and a negatively charged electron. This process is ionization, and the resulting soup of separate particles is a state of matter called plasma, which is transparent to light. The sheer scale at which a quasar performs this feat is what elevates it from a local phenomenon to a cosmic event. The intense ultraviolet radiation doesn't just ionize a few clouds nearby, it carves out a colossal sphere of influence in the intergalactic medium. Astronomers call this an ionization bubble or a Sturmgren sphere. Imagine a single, brilliant quasar acting as a lone, impossibly powerful street lamp in an otherwise dark and foggy field. Its light doesn't just pierce the fog in a narrow beam, it burns away the fog itself in a gigantic sphere centered on the lamp. The size of this transparent bubble is directly determined by the quasar's power. The brighter the quasar, the more hydrogen atoms it can ionize and the larger the bubble it can create. For the most luminous quasars, this bubble can stretch for tens of millions of light years, a volume of space so immense it could contain thousands of galaxies, all rendered transparent by the central beacon's relentless ultraviolet glare. This local effect provides astronomers with an invaluable laboratory for studying one of the most pivotal epochs in cosmic history, the epoch of reionization. This was the universal transition, which occurred when the universe was a few 100 million to 1 billion years old, when the pervasive fog of neutral hydrogen was permanently burned away by the light from the first stars and galaxies, rendering the universe transparent to ultraviolet light as it is today. We cannot watch that global process unfold in real time, but we can study a modern, localized analog of it happening right now around a distant quasar. By observing a quasar's ionization bubble, we can investigate the physics of how radiation interacts with the intergalactic medium. We can measure the density and clumpiness of the primordial hydrogen gas by seeing how sharply or diffusely the edge of the ionization bubble is defined. It's like studying how a flame burns through different types of material. The pattern of the burn edge tells you about the material's properties. The way we detect these bubbles is a triumph of observational astronomy. It involves a phenomenon known as the Lyman alpha forest, which we've touched on before. When we look at the spectrum of a distant quasar, we see a dense forest of dark absorption lines. These are created by countless clouds of neutral hydrogen gas at different distances between us and the quasar, each absorbing a specific wavelength of the quasar's light. However, if a quasar has ionized a giant bubble around itself, something remarkable happens in its spectrum. For a specific stretch of wavelengths corresponding to the vast region within the ionization bubble, the forest of absorption lines completely disappears. It's as if you were looking at a densely wooded hillside through a telescope and suddenly saw a perfectly circular, empty clearing, completely devoid of trees. This Lyman alpha trough is the direct signature of the quasar's cleansing effect. The absence of absorption lines tells us that within that volume, there is no neutral hydrogen left to absorb the light. The quasar has turned it all into transparent plasma. By measuring the width of this trough in the spectrum, astronomers can directly calculate the physical size of the ionization bubble, giving them a precise measure of the quasar's total ionizing power over its entire lifetime. The implications of this extend far beyond the bubble itself. This process demonstrates a critical form of quasar feedback on the largest possible scale. By ionizing the hydrogen in its vicinity, the quasar is not just clearing a window for our view, it is permanently altering the ecology of its cosmic neighborhood. Neutral hydrogen gas is the primary raw material for forming new stars. By ionizing this gas, the quasar effectively shuts down star formation, not only within its own galaxy, but potentially in all the smaller, satellite galaxies throughout the entire volume of its bubble. The gas is too hot and diffused to collapse and form new stars. This is feedback on an intergalactic scale, a demonstration of how a single, brilliant engine can dictate the developmental future of an entire protocluster of galaxies, suppressing the birth of new stars and influencing the type of galactic structures that will eventually emerge. The quasar's light pollution is therefore not just a side effect. It is an active and dominant force in the cosmic landscape, a temporary but incredibly influential phase that helps write the rules for how galaxies grow and evolve within the largest structures in the universe. But lurking within this chaotic whirlpool and these focused jets is an invisible architect, a force that orchestrates much of the spectacle we observe. This brings us to a fact that reveals the hidden strings pulling the levers of these cosmic powerhouses. The magnetic fields threading through a quasar are immensely powerful. We often think of gravity as the sole master of the black hole's domain, but within the frenzied plasma of the accretion disk and the focused jets, magnetism reigns as an equal and essential partner, a fundamental force without which the most spectacular displays of a quasar would simply fizzle out. To grasp the sheer scale of this magnetic power, we need to move beyond the simple bar magnets of a school science lab. The magnetic fields within a quasar are generated by the motion of the superheated, ionized gas in the accretion disk itself. As this churning, electrically conductive plasma swirls at near light speeds, it acts like a colossal natural dynamo, amplifying weak, initial magnetic fields into cosmic-scale structures of unimaginable strength. The energies involved are so vast that these fields can be billions or even trillions of times stronger than Earth's magnetic field. They are not uniform lines but are twisted, wound up, and stretched by the differential rotation of the disk, storing titanic amounts of energy like a coiled spring waiting to be released. This magnetic energy is not a passive bystander. It is a primary fuel for the entire system, an active participant in the conversion of gravitational energy into the brilliant light and furious outflows that define a quasar. One of the most profound roles these magnetic fields play is in the extraction of rotational energy from the black hole itself, a mechanism known as the Blandford-Zeenagic process. A spinning black hole drags the very fabric of spacetime around with it, a phenomenon called frame dragging. This rotating spacetime can act like a gigantic conductor, and if it is threaded with powerful magnetic field lines anchored in the surrounding accretion disk, a remarkable thing happens. The spinning geometry of the black hole can effectively generate a tremendous voltage difference, turning the entire system into a universe-class electrical generator. This process pulls rotational energy directly from the black hole and uses it to power the relativistic jets that blast from its poles. It's as if the black hole's spin is a colossal battery, and the magnetic fields are the wires that tap into it, channeling that raw power into focused beams of plasma that can stretch for millions of light years. Without this intricate magnetic coupling, a black hole would be a much less efficient engine, and the most powerful, radio-loud quasars with their spectacular jets might not exist at all. Beyond powering the jets, these magnetic fields are also the master sculptors that give the jets their iconic, needle-like form. A jet of plasma emerging from a chaotic accretion disk would naturally want to expand and dissipate in all directions, like smoke from a chimney dispersing in a gentle wind. But the magnetic fields surrounding a quasar prevent this. They act as a tight, invisible collar, channeling and confining the jet into an incredibly narrow and stable beam. This process, known as collimation, is what allows the jets to remain focused over distances that dwarf their host galaxies. The magnetic field lines are like the rails of a particle accelerator, guiding the charged particles and preventing them from straying sideways, ensuring the energy is delivered over immense cosmic distances to create the giant radio lobes we observe. It is this magnetic focusing that turns a potential diffuse cloud of hot gas into a cosmic blowtorch capable of writing its signature across intergalactic space. The influence of these fields doesn't stop at the large scale. They also govern the turbulent weather within the accretion disk itself. The magnetic fields are constantly being stretched, twisted, and tangled by the differential rotation of the disk. This builds up immense stress, much like winding up a rubber band, until the field lines suddenly snap and reconnect in violent events known as magnetic reconnection. These are colossal short circuits that release a flood of energy, rapidly heating the surrounding plasma and accelerating particles to near light speeds in dramatic flares. This process is a primary source of the high-energy X-rays we detect from quasars and is likely responsible for much of the rapid flickering and variability we observe. The magnetic field, therefore, is the dynamic heart of the storm, the engine of both the steady, colossal power of the jets and the sudden, brilliant flashes from the disk, orchestrating the entire brilliant and violent symphony of the quasar from behind the curtain. Now we can literally turn the universe's most powerful flashlights around and use them to illuminate the darkness in a completely new way. Fact 37 reveals a brilliant reversal of perspective. Quasars can be used as cosmic backlights to study faint, intervening galaxies. Instead of just focusing on the brilliant beacon itself, astronomers can use the quasar's intense beam of light as a tool to investigate the shadowy structures that lie in the foreground, galaxies that are often far too dim and distant to be studied directly with our current telescopes. It's a technique that transforms a potential obstacle into an unprecedented opportunity, allowing us to conduct a detailed forensic analysis of galaxies we might otherwise never even know existed. The method hinges on a simple but powerful principle of light. When the light from a distant quasar on its multi-billion-year journey to Earth happens to pass directly through the diffuse outer halo of a foreground galaxy, it doesn't just continue on its way unchanged. The gas, dust, and various chemical elements within that intervening galaxy leave their unique fingerprints on the quasar's light. As the light pierces through this galactic material, specific atoms and molecules absorb very particular wavelengths, creating a series of dark lines in the quasar's otherwise smooth and bright spectrum. This process is known as quasar absorption line spectroscopy, and it's like holding a pristine, brilliant light bulb behind a stained glass window that you cannot see directly. By carefully analyzing the intricate patterns and colors missing from the light, you can deduce the exact composition, shape, and even the motion of the invisible stained glass itself. What makes this technique so incredibly powerful is the sheer detail it can reveal. A direct image of a faint, distant galaxy might show us nothing more than a faint, fuzzy smudge of light. But its absorption signature imprinted on a quasar's spectrum is a rich and detailed dossier. Each set of absorption lines acts as a barcode identifying a specific chemical element: hydrogen, carbon, oxygen, magnesium, iron, and many others. The exact pattern and strength of these lines tell astronomers not only which elements are present in the intervening galaxy's halo, but also in what quantities. This provides a direct measurement of the galaxy's chemical enrichment, revealing how many generations of stars have lived and died within it, seeding its gas with heavier elements. A galaxy with strong lines from elements like iron and oxygen has been heavily processed by stars, while one with a spectrum dominated by pristine hydrogen is likely much more primitive, a cosmic relic from an earlier time. Beyond just a static chemical census, this method can also reveal the dynamic motions within these elusive galaxies. The absorption lines are not always perfectly sharp. They are often broadened, split, or shifted. If the gas in the foreground galaxy is turbulent or rotating, it will create a complex blend of absorption features at slightly different wavelengths. By deconstructing this blend, astronomers can map the velocity structure of the gas, discerning how it is moving within the galaxy's halo. They can identify massive outflows of material being driven by stellar winds or a central quasar, or trace the gentle inflow of intergalactic gas that fuels future star formation. In one spectacular observation, the light from a single background quasar can provide a multi-point probe of the foreground galaxy's gaseous environment, giving us a dynamic, three-dimensional understanding of its structure and evolution that a simple photograph could never hope to achieve. The serendipity involved in these discoveries adds another layer of wonder. Astronomers surveying the sky for quasars have no way of knowing in advance which of their targets will also serve as perfect backlights for an unseen galaxy. It is only after they take a spectrum and see the unexpected forest of absorption lines that the hidden structure reveals itself. This makes every new quasar spectrum a potential treasure map pointing toward a previously invisible galactic system. Over time, by collecting thousands of these chance alignments, scientists can build up a statistical picture of the population of typical galaxies across cosmic time, especially the low-mass, dim dwarf galaxies that are the most common type in the universe but also the most difficult to detect directly. This technique allows us to take a census of the cosmic population, not by seeing every individual, but by studying the shadows they cast on the brilliant stages of the most distant quasars, filling in the gaps in our understanding of how ordinary galaxies, and not just the brilliant giants, have evolved over the history of the universe. But to truly understand the significance of a quasar, we need to see it not as an isolated phenomenon, but as part of a vibrant cosmic family. This brings us to fact 38. Quasars are part of a wider supermassive family that includes their dramatic relatives, blazars, and Seyfert galaxies. Think of them all as different models of the same fundamental cosmic engine, a supermassive black hole actively feeding on its surroundings. What makes them appear so different to us, some as brilliant, star-like points, others as violently flickering monsters, and still others as the bright cores of familiar, nearby galaxies, often comes down to a simple twist of perspective, combined with the raw power of the central engine itself. First, let's meet the most extreme and volatile members of this family, blazars. In many ways, a blazar is essentially a quasar, but with one crucial, spine-tingling difference. We are staring directly down the barrel of its most powerful weapon. Remember those colossal, relativistic jets of plasma that some quasars fire from their poles? In a blazar, one of those jets is aimed almost perfectly straight at Earth. This unique viewpoint transforms its entire appearance and behavior. Because we are looking straight into the jet, its emission is massively amplified and beamed directly at us, making the blazar appear far more luminous than it would from any other angle. Furthermore, the material within that jet is moving at over 99.9% of the speed of light. As these ultra-relativistic particles stream toward us, their light is bunched up and intensified by an effect called relativistic beaming, turning the blazar into one of the most persistently bright and variable objects in the entire sky. They can flare up dramatically in a matter of hours, outshining everything else in their wavelength, from radio waves to the most energetic gamma rays, making them the unpredictable rock stars of the active galaxy world. Now, let's travel to the other end of the family spectrum and visit the quieter, but no less important cousins, Seyfert galaxies. Discovered by Carl Seyfert in the 1940s, these objects provide a crucial, nearby laboratory for studying the active galactic nucleus phenomenon. A Seyfert galaxy looks very different from a distant quasar. Instead of a single, star-like point, you see a beautiful, majestic spiral or elliptical galaxy, and nestled right at its heart is an intensely bright, star-like nucleus. The key distinction here is one of sheer power. Seyfert galaxies are the low-luminosity cousins of quasars. Their central black holes are typically less massive, often in the range of millions rather than billions of solar masses, and they are accreting material at a much more modest, steady rate. This results in a core that is brilliantly active and can still outshine its host galaxy stars, but it doesn't possess the staggering, universe-spanning luminosity of a full-blown quasar. What makes Seyfert so invaluable is their proximity. Because they are relatively close to us, we can study the intricate structure of their host galaxies, their swirling gas disks, and the subtle effects of their central engines with a level of detail that is impossible for their more distant, brilliant relatives. So, what ultimately determines whether a galaxy's core becomes a brilliant quasar, a dazzling blazar, or a steady Seyfert? The answer lies in a combination of two key ingredients: the mass of the central black hole and its accretion rate. A supermassive black hole of billions of solar masses, gorging on matter at a ferocious pace, has the potential to become a quasar. Whether we then classify it as a standard quasar or a blazar depends entirely on the orientation of its jet system relative to our line of sight. If its jets are pointed off at some angle, we see a standard quasar. If we are staring straight down the jet's throat, we call it a blazar. On the other hand, a galaxy with a smaller, million solar mass black hole that is feeding at a more leisurely, sustainable rate will manifest as a Seyfert galaxy. This beautiful continuity, known as the unified model of active galactic nuclei, tells us that we are not looking at fundamentally different beasts, but rather different expressions of the same incredible physical process, viewed from different angles and operating at different power levels. This entire family, from the brilliant quasars at the edge of time to the Seyferts in our cosmic backyard, is connected by the same violent, beautiful physics of matter surrendering to gravity's ultimate grip. This brings us to a crucial piece of the cosmic origins puzzle, a theory that attempts to solve the riddle of how these billion solar mass giants appeared so early. Fact 39 is about the intense, ongoing hunt for direct collapse black hole seeds. We've discussed the staggering scale of the problem: black holes of impossible size existing when the cosmos was barely out of its infancy. The idea of a direct collapse black hole provides a truly elegant and powerful solution. The theory proposes that the very first black hole seeds didn't come from the death of a single massive star. Instead, they formed through a far more dramatic and wholesale process: the catastrophic collapse of an entire primordial gas cloud, skipping the star-forming stage completely. To understand why this is such a compelling idea, let's contrast it with the traditional path. The standard model starts with a massive star, perhaps a few hundred times the mass of our Sun. When this star ends its short, brilliant life in a supernova, it leaves behind a black hole remnant of a few dozen solar masses. This is a tiny seed. For this seed to grow into a billion solar mass monster in less than a billion years, it would have to consume matter at its maximum possible rate for its entire existence, a frantic and seemingly unsustainable pace. It's like trying to grow a giant redwood tree from a mustard seed in a single summer. The growth required is just too frantic. The direct collapse model, however, offers a much more plausible head start. Imagine if that first seed wasn't a mustard seed but a full-grown sapling. In this scenario, a vast cloud of pure hydrogen and helium, perhaps containing the mass of 100,000 suns, collapses directly under its own immense gravity. Without the heavy elements that help modern gas clouds fragment into many smaller stars, this pristine cloud could collapse as a single, monolithic entity, resulting in the instantaneous birth of a black hole with an initial mass of 10,000, 100,000, or even a million solar masses. This is no longer a seed, it's a sapling, a gravitational titan ready to dominate its surroundings from day one. The environment required for this to happen is as specific as it is extreme. Astronomers believe direct collapse could only occur in rare, special regions of the early universe. These were likely areas bathed in the intense, sterilizing ultraviolet light from a nearby, massive primordial star or a young galaxy. This powerful external radiation would prevent the massive gas cloud from cooling efficiently and breaking apart. It would keep the cloud's chemistry simple, preventing the formation of hydrogen molecules that facilitate cooling and fragmentation. The cloud, unable to splinter, would remain a single coherent mass, growing ever denser and hotter until its internal pressure could no longer support its own weight. The entire structure would then succumb to gravity, collapsing directly into a black hole without ever igniting sustained nuclear fusion. It's a cosmic shortcut, a way for nature to fast-track the creation of the gravitational anchors around which the first giant galaxies would eventually assemble. This is where the revolutionary power of the James Webb Space Telescope enters the story. For decades, the direct collapse black hole was a beautiful but entirely theoretical idea. We had no way to observe these objects, as they would be incredibly faint and exist in an epoch of the universe shrouded in hydrogen fog. But Webb, with its unparalleled infrared sensitivity, was built to pierce that very fog. Astronomers are now using it to conduct a grand cosmic treasure hunt, scanning the deepest reaches of space and time for the unique signature of a direct collapse seed. What would such an object look like? It wouldn't be a brilliant quasar yet, as it hasn't had time to build a large, luminous accretion disk. Instead, it would appear as a very red, very compact object. Its light would be dominated by the glow of the heated gas directly falling into it, and its spectrum would show telltale signs of pristine gas, devoid of the heavy elements that are the pollution from generations of stars. Finding just one confirmed candidate would be a monumental discovery, providing the missing link that explains the rapid rise of the universe's first supermassive black holes, and finally solving the mystery of the impossibly large toddlers we see shining from the edge of time. Imagine the fabric of the cosmos as a vast, perfectly still, elastic trampoline. If you place a single, heavy bowling ball in the center, it creates a deep, smooth depression in the surface. This is a two-dimensional analogy for what mass does to our four-dimensional reality. It creates a curvature in space-time itself. Now, at the heart of a quasar, we don't have a bowling ball. We have a supermassive black hole with the weight of billions of suns, a gravitational anchor so profound it doesn't just create a dip in the cosmic trampoline, it punches a hole through it, dragging the very fabric of reality down into a bottomless well. This is the core of Einstein's general relativity made manifest. Mass doesn't just exert a force, it directly dictates the geometry of the universe, telling spacetime exactly how to curve. The quasar's central black hole is the ultimate cosmic sculptor, warping the stage upon which everything else must perform. This profound curvature has dramatic and measurable consequences for anything unfortunate enough to venture near it. Stars and vast clouds of gas that orbit the galactic center do not travel in simple, predictable ellipses like the planets in our solar system. Instead, they are forced to follow complex, Rosetta-like paths dictated by the severe warp in spacetime. It's as if they are marbles rolling around the steep, funnel-shaped depression created by our cosmic bowling ball. Their trajectories are permanently altered by the shape of the surface itself. This isn't a force acting at a distance in the Newtonian sense. It is matter simply following the most direct path through a curved geometry, a path known as a geodesic. The more extreme the curvature, the more bizarre the orbital paths become. For matter spiraling into the accretion disk, this warping is the engine of its doom, the reason it can be heated to millions of degrees and ultimately provide the blinding luminosity of the quasar. The motion of stars and gas in this region provides astronomers with direct evidence of the black hole's mass and the intense gravitational landscape it commands, a landscape where the familiar rules of flat space no longer apply. Perhaps the most visually stunning result of this spacetime warping is the phenomenon of gravitational lensing. As the brilliant light from the quasar's accretion disk travels outward, it must climb out of this immense gravitational well. According to Einstein's theory, the path of the light itself is bent by the curvature. Think of it as a beam of light trying to travel in a straight line across the surface of our deeply curved trampoline. Its path is inevitably deflected. In extreme cases, this can create spectacular optical effects, like the Einstein cross we discussed earlier, where a single quasar is split into multiple images. But even on a more subtle level, this lensing effect acts as a natural magnifying glass. It can slightly amplify the quasar's light, making it appear brighter than it otherwise would, and it can distort the faint image of the quasar's host galaxy, stretching it into faint, ethereal arcs. This isn't a trick of the atmosphere or a flaw in our telescopes. It is the universe faithfully following the rules of general relativity, using the gravity of the most massive objects to literally reshape our view of the cosmos. We can push this concept to its absolute limit by considering the fate of the light emitted from the accretion disk itself. The innermost stable orbit of the disk is the very edge of the precipice, the last point from which light can still escape the black hole's gravitational clutches. Photons generated here are fired in every direction, but those aimed slightly inward are forever lost. Those aimed outward must make a desperate climb. As they struggle up the steep curvature of space-time, they lose energy, their wavelength stretching in a dramatic display of gravitational redshift. The light we finally receive from this region has been fundamentally altered by its journey, carrying the unmistakable fingerprint of its escape from an extreme gravitational field. By analyzing this light with incredible precision, astronomers can essentially map the shape of the space-time warp around the black hole, testing the predictions of general relativity in an environment 1,000,000 times more powerful than our solar system. Every flicker and every color of a quasar's light is therefore a message, not just about the hot gas that emitted it, but about the twisted geometry of the universe itself, a geometry carved by the most concentrated mass the cosmos can produce. When we speak of the incredible winds flowing from a quasar, we are venturing into a realm of physics that challenges our everyday understanding of speed and power. Fact 41 reveals an almost unbelievable characteristic of these outflows. They can reach relativistic speeds. This means the material isn't just moving quickly in an astronomical sense. It is traveling at a significant fraction of the speed of light itself. We are not talking about a gentle breeze or even a terrestrial hurricane, but a supersonic tempest of ionized gas accelerated to velocities that can exceed 20, 40, or even 60% of light speed. To put that into a tangible number, that is over 180 million kilometers per hour. At that unfathomable velocity, you could travel from the Earth to the Sun in less than 30 minutes. This isn't a gentle flow, it is a fire hose of raw energy blasting its way through the galaxy. The engine capable of launching such a relativistic torrent lies deep within the quasar's central furnace. The primary mechanism is the intense radiation pressure generated by the brilliantly hot accretion disk. This disk emits a truly ferocious flood of ultraviolet and X-ray photons. Each of these photons carries a tiny amount of momentum, and when this relentless blast of energy slams into clouds of gas hovering near the black hole, it acts like a cosmic sandblaster. The photons physically push on the gas, transferring their momentum and accelerating the material outward. In the innermost regions where the gravitational pull is strongest and the radiation is most intense, this process can be incredibly efficient, launching material not just away from the disk, but propelling it to these mind-bending, relativistic velocities. It's a testament to one of the most fundamental principles in the universe. Light, despite having no mass, can exert a force powerful enough to hurl entire solar systems worth of matter across space at a substantial fraction of the universe's ultimate speed limit. The sheer energy carried by these ultra-fast outflows is what makes them a dominant force in shaping the entire life cycle of their host galaxy. The equation for kinetic energy is 1/2 the mass times the velocity squared. Because the velocity term is squared, even a modest amount of gas moving at relativistic speeds carries a staggering, almost inconceivable amount of destructive power. Astronomers calculate that these winds can carry kinetic energy equivalent to the total output of the quasar's light for thousands or even millions of years. This energy isn't just vanishing into the void, it is being dumped directly into the galaxy's interstellar medium. The impact is like setting off a continuous series of colossal bombs throughout the galactic core. This constant, violent agitation heats the surrounding gas to temperatures of millions of degrees, preventing it from ever cooling down, collapsing, and forming new stars. The galaxy's primary fuel supply for future stellar generations is effectively sterilized, cooked into a hot, diffuse plasma that is useless for star formation. This process, known scientifically as quenching, is the ultimate form of feedback from the central black hole. It solves a long-standing puzzle in cosmology: why the most massive galaxies in the universe are largely devoid of vibrant, young blue stars and are instead dominated by older, redder stellar populations. The quasar, in its brilliant and violent youth, uses these relativistic winds as a self-regulating mechanism. As the black hole feeds and grows brighter, it powers these immense outflows. Those outflows then blast away or heat up the very gas that was feeding the black hole in the first place, eventually starving the engine and causing the quasar phase to shut down. The galaxy's growth is halted, its star-forming days effectively over, the central black hole, having gorged itself and then blown away its own dinner table, enters a long, quiet dormancy. These relativistic winds are therefore not merely a spectacular side effect. They are the central governor in a cosmic balancing act, a key reason why galaxies don't grow infinitely large and why the universe has the rich diversity of galactic types we observe today. This remarkable ability to peer across billions of years brings us to a truly synthesizing fact, one that encapsulates the entire purpose of this cosmic quest. Fact 42. These distant beacons are, in effect, time machines for galactic evolution. They offer us more than just isolated snapshots of the early universe. They provide the individual frames for a grand cosmic movie, allowing us to watch the entire life story of a massive galaxy unfold. By simply observing quasars at different distances and therefore from different cosmic epochs, we can assemble a chronological sequence, witnessing firsthand how a galaxy and its central supermassive black hole grow up together, locked in a complex gravitational dance that dictates their shared destiny. Think of the cosmos as a vast museum displaying portraits of the same person at every stage of life. In one wing, we have the brilliant, chaotic quasars from when the universe was less than 1 billion years old. These are the portraits of galactic infancy, full of raw energy and rapid growth. In another wing, we see quasars from cosmic noon, around 10 billion years ago, a period of peak activity and bustling construction. Further along, we find quieter, more settled active galaxies from more recent times. And finally, in our own local universe, we see the end result: majestic, mature galaxies like Andromeda and the Milky Way, with their central black holes now dormant. We cannot follow a single galaxy for 13 billion years, but by studying this cosmic gallery of quasars, we can reconstruct the entire life cycle, connecting the dots from the violent, brilliant beginnings to the calm, stately present. The central, unifying plot of this cosmic movie is the profound connection between the black hole and its galaxy. For a long time, astronomers viewed these as separate entities, but the story told by quasars reveals an intimate, co-evolutionary relationship. The data shows a surprising and consistent correlation. The more massive a galaxy's central bulge of stars is, the more massive its central black hole tends to be. This is not a coincidence, it is a signature of a shared history. The violent quasar phase appears to be the key mechanism that forges this link. During this period, the black hole feasts on galactic material, growing in mass while simultaneously unleashing tremendous energy in the form of radiation and relativistic winds. This energetic feedback acts as a cosmic regulator, blowing away the galaxy's gas reserves and quenching further star formation. The galaxy's growth is halted, and the final mass of its stellar population is set, all while the black hole's own growth is ultimately limited by the lack of remaining fuel. The quasar phase is the pivotal, transformative event that synchronizes their development, ensuring they grow in lockstep. This narrative fundamentally alters our understanding of our own cosmic home. The quiet, supermassive black hole at the center of the Milky Way, Sagittarius, a star, is not an anomaly. It is the retired engine of a bygone era. Our galaxy, now a relatively peaceful spiral, almost certainly hosted its own brilliant quasar phase billions of years ago. That period of violent activity, driven by mergers or intense inflows of gas, would have shaped the very structure we see today. The quasar's powerful winds likely blew away leftover gas, helping to create the clear, defined spiral arms and preventing our galaxy from becoming an even more massive, formless elliptical. The mass of our central black hole, over 4 million suns, is a direct relic of that ancient feast, a fossilized testament to the brilliant, violent youth that shaped the galaxy we now call home. When we look at the most distant quasars, we are not just studying abstract, alien phenomena. We are witnessing the fiery, formative years of our own galactic ancestry, a chapter written in light across the vastness of space and time. But the brilliant, steady glow we often picture is just an average, a composite of countless smaller, violent events happening deep within the whirlpool of matter itself. Fact 43 reveals a more dynamic reality. The accretion disk can pulse within falling matter. Rather than a smooth, river-like flow of gas into the central engine, the process is often far more chaotic and lumpy, resembling a torrential downpour where large droplets intermittently strike a pond's surface. These aren't gentle ripples, they are significant splashes of matter that, when they finally plunge into the inner disk, cause the entire quasar to temporarily flare up in a distinctive pulse of increased brightness, a momentary surge in its already staggering luminosity. This clumpy accretion is a direct result of the complex physics governing the fuel supply. The vast reservoirs of gas that feed a supermassive black hole are not uniform. They are filled with density variations, denser clouds, and more diffuse regions, all orbiting the center of gravity. As these clouds travel inward, they don't just merge seamlessly into the main disk. Instead, they can maintain their integrity for a time, eventually striking the outer edge of the accretion disk like a series of celestial comets impacting a gaseous planet. When a particularly large and dense clump, containing perhaps the mass of several Jupiters or even a small star, finally makes contact, it delivers a sudden, concentrated infusion of fuel. This extra mass disturbs the delicate equilibrium of the disk, creating a shock wave that rapidly heats the local region and triggers a spike in energy production before the material is assimilated and smoothed out by the disk's relentless rotation. These events are the individual heartbeats of the quasar, brief but telling moments of heightened activity against the background roar of the continuous feast. We can visualize this with a practical analogy. Imagine you're trying to fuel a massive industrial furnace. If you have a conveyor belt steadily feeding a constant stream of coal into the fire, the furnace will burn with a stable, intense flame. But if, instead, workers periodically toss in entire large wheelbarrows full of coal all at once, the fire will momentarily roar with a much greater intensity, sending up a huge plume of sparks and heat before settling back to its baseline. In the cosmic context, the steady conveyor belt represents the smooth, continuous flow of gas, while the wheelbarrow dumps are the dense clumps of matter causing the observed pulses in the quasar's light output. For astronomers, these pulses are far more than just a curiosity. They are a powerful diagnostic tool, a form of cosmic sonar that lets us map the invisible structure of the accretion disk. The key lies in a technique called reverberation mapping. When a pulse of increased brightness occurs in the innermost, hottest part of the accretion disk, it sends a flash of high-energy radiation like an ultraviolet or X-ray flare outward in all directions. This flash then travels at the speed of light to illuminate gas clouds farther out in a region known as the broad line region. When the light from these now energized clouds finally reaches our telescopes, there is a measurable time delay between the initial flare in the disk and the subsequent brightening of the emission lines from the gas. This delay is literally the light travel time from the central engine to the broad line gas. By carefully measuring these time lags across different wavelengths of light, which originate from different distances from the black hole, scientists can effectively triangulate the size and geometry of the entire accretion structure, turning the flickering light of a quasar into a detailed three-dimensional map of its most central regions. Furthermore, studying the rise and fall time of these pulses provides a direct window into the hydrodynamics of matter under the most extreme gravitational conditions imaginable. The duration of a pulse tells us about the size and density of the infalling clump, while the way the pulse spreads out and fades reveals how energy and angular momentum are transported through the turbulent plasma of the disk. It's like studying how a splash evolves in a whirlpool. The pattern of the ripples tells you about the water's viscosity and the shape of the container. In the relativistic whirlpool around a black hole, matter is moving at a significant fraction of the speed of light and is subjected to intense magnetic fields and tidal forces that stretch and compress it. The behavior of these pulses allows theorists to test their most sophisticated computer simulations, checking whether their models correctly predict how real matter behaves when pushed to the absolute limits of physics, in an environment where Einstein's theory of general relativity is the dominant force. Each flicker, each pulse in the light of a quasar billions of light years away, is therefore a tiny, precious data point, a natural experiment that helps us understand the fundamental laws that govern the flow of matter and energy in the most violent and energetic corners of the universe. Now, let's place that staggering power into the wider context of cosmic cataclysms, because Fact 44 reveals a truly humbling comparison. These brilliant beacons can actually outshine even the most violently explosive events in the universe, gamma-ray bursts in total energy output over their lifetime. This statement might seem counterintuitive at first. After all, a gamma-ray burst, or GRB, is the single most luminous transient phenomenon we know of. In a matter of seconds, a GRB can release more energy than our Sun will emit over its entire 10 billion-year lifespan. It is a cosmic flashbulb, a blinding, momentary spike of pure power that, for a fleeting instant, can outshine every star in its host galaxy combined. But that keyword transient is the crucial distinction. A GRB is a spectacular but incredibly brief firecracker. A quasar, on the other hand, is a sustained, raging wildfire. To truly appreciate the difference, we need to think about energy not just in terms of peak brightness, but as a total quantity, the full power output integrated over time. Imagine the difference between a camera's flash and the steady, brilliant beam of a lighthouse. The camera flash is intensely bright, but it lasts for only 1/1000th of a second, releasing a fixed, finite amount of energy. The lighthouse beacon, while never reaching that same instantaneous peak, shines on relentlessly, night after night, year after year. Over the course of a single decade, that steady lighthouse will have emitted far more total light energy than that one brilliant flash ever could. This is the fundamental difference between a GRB and a quasar. A typical GRB might blaze with unimaginable fury for anywhere from a few milliseconds to a couple of minutes. A quasar, in contrast, maintains its incredible output for a staggering length of time, tens of millions, and often hundreds of millions of years. Let's put some numbers to this almost incomprehensible timescale. 100 million years is a duration so vast it defies human experience. It's a period in which continents can drift apart, mountain ranges can rise and erode away, an entire species can evolve and go extinct on a planet like Earth. For all that time, a quasar is pouring out the energy of 1 trillion suns, second after second, minute after minute, millennium after millennium. When you add up all that energy, this constant, prodigious output multiplied by an almost geological span of time, the total becomes mind-numbing. It surpasses the total energy of a gamma-ray burst by many orders of magnitude. To say it outshines a GRB in total energy is a dramatic understatement. It's like comparing the total heat given off by the Earth's core over billions of years to the heat from a single nuclear bomb detonation. Both are immense, but one is a foundational, persistent force, while the other is a fleeting, if spectacular, event. This profound difference in duration is the direct reason why quasars have such a transformative and lasting impact on their galactic environments, while GRBs are more localized disasters. A gamma-ray burst is a catastrophic sterilizing event. If one were to occur too close to a life-bearing planet, its intense radiation could wipe out the ozone layer and trigger a mass extinction. But its influence is fleeting. A quasar's impact is the exact opposite. It is a long-term, dominant force that governs the entire evolution of its host galaxy. The sustained power of a quasar is what fuels those colossal winds we discussed, winds that persist for millions of years, systematically scouring a galaxy of its star-forming gas. It is this relentless energy output that carves out those immense ionization bubbles in the intergalactic medium, transparent spheres that persist long after the quasar itself has faded. A GRB is a cosmic lightning strike, devastating but local and brief. A quasar is the climate itself, a permanent atmospheric condition that determines what can live and grow within its domain for eons. The sustained brilliance of a quasar is what allows it to act as the central architect of its galaxy, a force of creation and destruction whose legacy is written into the very stars and structure of the cosmos. And this leads us to a pivotal moment in modern astronomy, a revolution that is actively rewriting our understanding of the cosmic dawn. Fact 45. The James Webb Space Telescope is an absolute game-changer in the hunt for the most distant quasars. You see, for decades, our ability to peer back to the very first structures in the universe was fundamentally limited. The most ancient quasars, with their light stretched deep into the infrared by the expansion of the cosmos, were like whispers in a crowded room for telescopes designed primarily for visible light. They were either completely invisible or appeared as faint, blurry points, their vital secrets locked away in wavelengths we couldn't properly observe. But Webb was built from the ground up to be the ultimate infrared observatory, a perfect key for this cosmic lock. Its immense sensitivity and resolution at these specific wavelengths have flung open a window to the universe's infancy, allowing us to see these primordial beacons with a clarity we once only dreamed of. This new capability manifests in two spectacular ways. First, Webb is a prolific discoverer, a cosmic prospector uncovering brilliant gems in the deepest, darkest mines of space and time. It conducts deep field surveys, staring for long periods at seemingly empty patches of sky, and in doing so, it reveals quasars that are so distant and redshifted they are completely undetectable by any other instrument. Each new discovery pushes the frontier further back, giving us a fresh data point from an earlier moment in cosmic history, challenging our models of how quickly supermassive black holes could possibly form. But Webb's role goes far beyond simply adding new pins to the cosmic map. Its second, and perhaps even more profound, power is its ability to perform a detailed forensic analysis on the light from these distant quasars. With its sophisticated suite of spectrographs, Webb doesn't just see that a quasar is there. It meticulously dissects its light, spreading it out into an incredibly detailed infrared rainbow. This spectrum is a treasure trove of information, and Webb's precision allows us to read it like a high-resolution cosmic biography. Let's break down what this unprecedented detail actually reveals. One of the most crucial measurements is the mass of the central supermassive black hole itself. Webb can analyze the broad emission lines from the whirling gas in the quasar's broadline region. The width of these lines tells us the speed of the gas, and from that speed, using the laws of gravity, astronomers can calculate the mass of the central gravitational anchor. For the first time, we are getting reliable, precise weights for these black holes at the edge of time, confirming just how monstrous they truly were so early on. But Webb's vision goes even deeper, peeling back the overwhelming glare of the quasar's core to glimpse its host galaxy. This was nearly impossible before. the brilliant nucleus drowned out the faint, sprawling light of the infant galaxy around it. Now, Webb's infrared eyes and advanced coronagraphs can block that brilliant central point, revealing the faint, fuzzy halo of the host. We can finally study these nascent galaxies directly, measuring their size, their structure, and the rate at which they were forming stars, all while their central black hole was in the midst of its most violent and brilliant feeding frenzy. Perhaps one of the most exciting revelations involves the chemical composition of the gas in and around these systems. Webb's sensitive spectrographs can detect the faint absorption signatures of elements like carbon, oxygen, and nitrogen in the gas that surrounds the quasar and fills its host galaxy. Finding these metals, these elements forged in stars, in a universe that was less than 1 billion years old is a monumental discovery. It tells us unequivocally that the first generation of stars had already lived and died in spectacular supernova, polluting the primordial gas with the raw materials for future planets and life, all before these distant quasars even ignited. Webb is effectively taking a core sample of the early universe, and with each new quasar it observes, it adds another layer to our understanding of how the pristine cosmos transformed into the complex, chemically rich universe we inhabit today. This telescope is not just showing us the most distant quasars, it is allowing us to perform a full medical check-up on them, diagnosing their mass, studying their environment, and even conducting a blood test on their chemical makeup, all from a distance of over 13 billion light-years. Yet, for all their staggering might, these cosmic giants are not infinitely powerful. They are bound by the same fundamental laws of physics that govern the rest of the universe, and this brings us to a crucial regulatory principle. Fact 46. There is an ultimate ceiling to a quasar's brilliance, a concept known as the Eddington limit. This isn't just a theoretical curiosity. It is a fundamental physical break, a natural thermostat that prevents a supermassive black hole from consuming its entire galaxy in one frantic, uncontrolled binge. The Eddington luminosity represents the maximum stable brightness an object can achieve when the outward pressure of its own radiation perfectly balances the inward, crushing pull of gravity. Imagine a star so brilliantly hot that its light is physically pushing against its own outer layers, preventing it from collapsing. Now, scale that idea up to a supermassive black hole. The searing radiation pouring from its accretion disk doesn't just travel outward unimpeded. It slams into the surrounding clouds of gas and dust, and each photon of light carries a tiny amount of momentum, exerting a continuous outward pressure. This creates a delicate and dynamic balancing act. On one side, you have the black hole's immense gravitational pull, relentlessly dragging matter inward to feed the brilliant engine. On the other side, you have the incredible radiation pressure generated by that very infall, which pushes outward against the incoming fuel. The Eddington limit is the precise point where these two titanic forces are in equilibrium. If a black hole tries to accrete matter and shine brighter than this limit, the radiation pressure becomes so overpowering that it acts like a cosmic hurricane, effectively blowing the surrounding gas and dust away from the black hole. It's like a fire that burns so ferociously hot it creates its own gale force wind, scattering the very logs it needs to keep burning. In this scenario, the quasar literally chokes on its own brilliance, shutting off its own fuel supply and causing its dazzling light to dim until a new balance can be found. This is why we don't see quasars shining with infinite, ever-increasing luminosity. They are self-regulating engines constrained by this elegant and inescapable law of physics. The implications of this limit extend far beyond just capping brightness. It fundamentally governs the growth rate of the black hole itself. The Eddington limit sets a maximum speed for how quickly a black hole can gain mass. For a typical supermassive black hole of 1 billion solar masses, this maximum stable accretion rate is roughly equivalent to consuming 1 solar mass of material every single year. Now, this might sound like a gluttonous feast, and it is, but it's a controlled one. If the black hole were to consistently exceed this rate, it would continually blow away its fuel, preventing sustained growth. This physical ceiling is a key piece of the puzzle when we confront the existence of billion solar mass black holes in the very early universe. For them to have grown so large so quickly, they must have been feeding at or very near their Eddington limit for a significant portion of their early existence. Their growth was a frantic but regulated sprint, not a chaotic free-for-all. This limit provides a crucial benchmark for theorists, helping them test models of early black hole formation and determine whether exotic mechanisms like direct collapse or temporary bursts of super-Eddington accretion were necessary to explain the cosmic giants we observe. We can make this abstract concept more tangible by considering an example from our own cosmic neighborhood, or rather, the lack of one. The supermassive black hole at the center of our Milky Way, Sagittarius A star, is currently a very quiet and well-behaved engine. It is accreting matter at a rate thousands of times below its Eddington limit. This is why it's so faint. If, by some cosmic event, a vast cloud of gas were to be funneled directly into it, it would begin to shine more brightly. As its luminosity increased, so would the radiation pressure pushing back on the incoming gas. If the influx of fuel became too great, the system would reach its Eddington luminosity, and the resulting radiation pressure would violently expel the excess material, preventing a runaway explosion and maintaining a stable, if brilliant, equilibrium. This self-regulating mechanism ensures that black holes don't simply consume everything in one go. It forces their growth to be a punctuated process, with periods of brilliant feasting followed by quieter times of digestion, a cycle that ultimately shapes not only the black hole's own destiny, but the evolutionary path of the entire galaxy it calls home. Deep within the heart of a quasar, beyond the brilliant blaze of the accretion disk, lies a mysterious and seething component, the corona. Now, this isn't like the wispy, atmospheric halo surrounding our sun. A quasar's corona is a region of unimaginably ferocious energy, a tenuous soup of electrons heated to billions of degrees by processes we are still striving to fully understand. This superheated plasma, hovering just above and below the accretion disk, is the primary source of the powerful X-rays that stream from these cosmic engines. While the disk itself glows white-hot with intense thermal radiation in visible and ultraviolet light, the corona takes that energy and supercharges it, hammering the disk's photons into the most energetic part of the electromagnetic spectrum through a relentless process called inverse Compton scattering. But the corona is more than just a steady source of high-energy light. It is a dynamic and flaring beast, and its sudden outbursts create a remarkable opportunity for astronomers to perform a kind of cosmic echolocation, mapping the very architecture of the quasar's heart. This brilliant technique works by exploiting a fundamental cosmic speed limit, the speed of light itself. Imagine a scenario where a tremendous magnetic storm erupts within the corona, causing a sudden, brilliant flare in X-ray output. This flash of high-energy radiation explodes outward in all directions. Some of these X-ray photons travel directly toward our telescopes, giving us the initial signal of the flare. But a significant portion of this flash travels downward, striking the surface of the relatively cooler accretion disk below. When these energetic X-rays slam into the iron and other heavy elements in the disk, they don't just get absorbed, they deposit their immense energy, violently heating that specific patch of the disk and causing it to respond by glowing more brightly in ultraviolet light. This response is not instantaneous. There is a tiny but measurable time delay, the time it takes for the X-ray flash to travel from the corona down to the disk, plus the time for the newly energized ultraviolet light to travel back up and begin its journey across the universe toward us. This delayed ultraviolet glow is the echo of the original X-ray shout. For astronomers, this time delay is a gift of immeasurable value. by meticulously recording the moment of the initial X-ray flare and then carefully monitoring the quasar's ultraviolet light for the resulting echo, they can literally measure the distance between the corona and the part of the disk that was illuminated. It's a direct geometrical measurement. Think of it like judging the distance to a far-off canyon wall by shouting and timing how long it takes for the echo to return. In the cosmic version, the corona provides the shout and the accretion disk provides the canyon wall. By observing multiple flares and their corresponding echoes, scientists can triangulate the structure, mapping not just a single distance, but the overall size and shape of the entire inner accretion disk region. This method, known as X-ray reverberation mapping, transforms the flickering light of a quasar into a precise architectural blueprint of its most central components. The insights gained from this echoing phenomenon are profound. First and foremost, it provides one of the most direct and reliable measurements of the sheer scale of the accretion disk. The time delays observed are typically on the order of minutes to hours for stellar mass black holes, scaling up to days or even weeks for the supermassive black holes powering quasars. These measurements confirm that while these disks are cosmically compact, they are still vast structures, often extending to distances equivalent to the orbit of Jupiter or Saturn in our own solar system, all while containing the mass of billions of suns. Furthermore, by seeing which parts of the disk light up first and how the echo propagates, astronomers can probe the disk's geometry. Is it a perfectly flat plate, or is it warped and twisted by the black hole's immense spin? The pattern of the echoes holds the answer, revealing the true topography of space-time around the black hole and providing yet another stringent test for Einstein's theory of general relativity in the most extreme environment the universe can provide. So now we arrive at a fact that places these brilliant beacons at the very center of one of the most profound transformations in cosmic history. Fact 48. Quasars are key to understanding the epoch of reionization. To grasp what this means, we have to rewind the cosmic clock to a time before the first galaxies and quasars fully formed, to a universe that was fundamentally dark and opaque. After the brilliant flash of the Big Bang faded and the universe cooled, it entered a period often called the Cosmic Dark Ages. Space was filled with a thick, uniform fog of neutral hydrogen gas. Neutral hydrogen is notoriously efficient at absorbing energetic ultraviolet light, so the first stars and galaxies that began to ignite were largely shrouded from view, their light trapped within this pervasive cosmic mist. The universe was a prisoner inside its own gaseous shroud. The epoch of reionization was the great escape from this foggy prison. It was the pivotal era when the first luminous objects, those first massive stars, and crucially, the first quasars began to flood the cosmos with enough energetic radiation to fundamentally change the state of the intergalactic medium. The process is called ionization, and it works like a cosmic-scale cleaning operation. When a high-energy ultraviolet photon from a young, hot star or a brilliant quasar slams into a neutral hydrogen atom, it delivers such a powerful kick that it knocks the atom's single electron clean off its nucleus. This transforms the atom from a neutral particle into a free proton and a free electron, creating a state of matter known as a plasma. This ionized plasma is transparent to light, unlike the opaque fog of neutral hydrogen. Over hundreds of millions of years, this process burned away the cosmic fog, clearing the universe and making it transparent to ultraviolet light for the rest of cosmic history, which is why we can see galaxies and quasars from so far away today. Now, while the very first population of massive stars undoubtedly began this monumental task, their collective light was often limited in its reach. These stars were scattered across the early cosmos, and their radiation could only clear relatively small, localized bubbles around them, like individual campfires struggling to push back a vast global fog. This is where quasars entered the stage as the ultimate game changers. A single, brilliant quasar is not a campfire, it is a colossal cosmic searchlight. Its intense, focused beam of ultraviolet and X-ray radiation is millions of times more powerful than the combined output of an entire young galaxy of stars. This gave quasars a unique and devastatingly efficient ability to carve out immense ionization bubbles in the neutral hydrogen, where a cluster of early stars might clear a region a few thousand light-years across. A powerful quasar could blast a transparent void stretching for tens of millions of light-years, a volume of space so vast it could contain thousands of nascent galaxies. We can actually observe the ghostly remnants of this process by studying the light from the most distant quasars themselves. As we've discussed, their spectra show a dense Lyman alpha forest of absorption lines created by the remaining clumps of neutral hydrogen their light passes through. However, for quasars that lived during the tail end of reionization, something remarkable appears in their spectra, a vast, clean stretch with no absorption lines at all, known as a Gunn-Peterson trough. This trough is the direct signature of the quasar's own local work. It signifies that for a certain portion of its light journey, it traveled through a volume of space that the quasar itself had completely ionized. There was simply no neutral hydrogen left to absorb the light, creating a silent, empty channel in the spectrum that speaks volumes about the quasar's cleansing power. By measuring the size of these troughs, astronomers can directly gauge the scale of a quasar's influence, effectively measuring the size of the transparent bubble it blasted out of the primordial fog. The role of quasars, therefore, was likely not to start the reionization process but to finish it. They were the cosmic cleanup crew, the heavy artillery that dealt with the most stubborn, dense pockets of neutral hydrogen that the first stars couldn't handle. Their intense radiation could penetrate deeper into the fog and ionize vaster volumes than anything else in the universe. By completing the process, they ensured that the universe became permanently transparent, allowing light to travel freely across cosmic distances and setting the stage for the golden age of galaxy formation that followed. Without the decisive contribution of these early quasars, the universe might have remained patchy and foggy for much longer, dramatically altering the timeline for the growth of cosmic structure and potentially delaying the arrival of the clear, star-filled cosmos we are so fortunate to observe today. Now, this brings us to a pivotal moment in the history of astronomy, a discovery that turned a compelling theory into an inescapable conclusion. The incredibly rapid variability in a quasar's brightness provided what many consider to be the smoking gun for the existence of supermassive black holes. For a long time, the idea of million or billion solar mass black holes was viewed by many in the scientific community as a mathematical fantasy, a theoretical possibility too extreme to actually exist in nature. The staggering energy output of quasars was a profound puzzle, but the final, most convincing piece of evidence came not from their immense power, but from the speed at which that power could change. Astronomers monitoring these objects noticed that their brightness could fluctuate significantly over surprisingly short periods, sometimes in a matter of days, weeks, or months. This wasn't a gradual dimming over centuries, it was a rapid flickering, a cosmic heartbeat emanating from the very core of the engine. The significance of this flickering lies in a fundamental limit set by the universe itself, the speed of light. In physics, no signal, no change, no information can travel faster than light. This simple fact places a strict constraint on the size of any object that varies in brightness. Imagine a light bulb that is 1 light-year across. If you could magically switch it on all at once, an observer would see the side nearest them light up immediately, but it would take a full year for the light from the far side to reach them. The object couldn't possibly appear to brighten or dim as a whole any faster than the time it takes light to cross its entire diameter. Therefore, the faster an object varies, the smaller its light-emitting region must be. When astronomers applied this logic to quasars, the results were staggering. The fact that a quasar's luminosity could double or halve in a matter of weeks meant that the phenomenally powerful engine driving it had to be smaller than our own solar system. Here was an object unleashing the power of 1 trillion suns from a volume of space that could comfortably fit inside the orbit of Pluto. This combination of attributes was simply impossible to explain with any known celestial object. A cluster of millions of stars packed that tightly would instantly collapse under its own gravity. A single supermassive star was not only unstable but couldn't account for the broad emission lines and the incredible energy efficiency. The only conceivable object in the universe that could pack a mass of billions of suns into a region the size of a solar system, creating a gravitational field so intense that it could power such a brilliant and rapidly varying beacon, was a supermassive black hole. The rapid variability was the crucial clue that sealed the deal. It wasn't just that a black hole was a possible explanation, it became the only viable explanation. The flickering light was the signature of the chaotic, stormy accretion disk, where magnetic flares and instabilities near the event horizon caused the brilliant glow to pulse and shudder. Its changes limited only by the tiny orbital periods in that extreme gravitational environment. This observational evidence, when combined with the theoretical models of gravitational energy release from accretion, formed an airtight case. Quasars were no longer mysterious quasi-stellar objects. They were the brilliant, active nuclei of galaxies, powered by the gravitational surrender of matter to the most profound pits of darkness in the cosmos, and their variable light was the direct proof. And so we reach our final and perhaps most forward-looking fact. The current record for the most distant quasar will almost certainly be broken soon. The journey we've taken through these 50 facts is not the end of the story, but merely the latest chapter in a rapidly unfolding cosmic epic. The brilliant beacons we've identified at the edge of time are not the final frontier. They are the trailheads, marking the path for the next generation of explorers who will venture even deeper into the universe's primordial past. With each passing year, our technological grasp extends further, and the tools we are now bringing to bear promise to revolutionize our view of the cosmic dawn in ways we can only begin to imagine. At the forefront of this new era is the James Webb Space Telescope, an instrument that has already begun to shatter previous distance records, but its true potential is only just being unlocked. Webb's planned deep field surveys will stare for hundreds of hours into carefully selected patches of sky, gathering every precious photon of infrared light that has traveled for over 13 billion years. These are not mere snapshots, they are deep cosmic core samples drilling down through layer after layer of cosmic history. Where current observations might reveal a handful of candidate quasars from the universe's first billion years, Webb's unprecedented sensitivity is expected to uncover dozens, perhaps even hundreds of these ancient giants. Each new discovery will be a data point that helps us chart the rise of the first supermassive black holes with statistical confidence, moving from puzzling outliers to a clear population that we can analyze and understand. But the revolution doesn't stop in space. Here on Earth, the Vera C. Rubin Observatory, with its colossal 3.2 billion pixel camera, is poised to begin the legacy survey of space and time, or LSST. This monumental project will photograph the entire available sky every few nights for a decade, creating an unprecedented motion picture of the cosmos. While Webb peers deeply into tiny, key areas, Rubin will cast an immensely wide net, scanning the entire heavens for the telltale flicker of distant quasars. Its automated systems will identify millions of active galactic nuclei, sifting through this ocean of data to find the rarest gems, those few, incredibly red points of light whose extreme redshift marks them as candidates from the very earliest times. Rubin will provide the treasure map, and Webb will then be tasked with focusing its powerful infrared eyes on the most promising X's to confirm their nature and study them in exquisite detail. The ultimate goal driving this global astronomical effort is as profound as it is clear: to find the very first quasars and black holes, those that ignited when the universe was a mere 200 to 300 million years old. This is the true cosmic frontier, an era known as the Cosmic Dawn, when the first large-scale structures were just beginning to coalesce from the primordial darkness. Discovering a quasar from this epoch would be one of the most significant achievements in the history of cosmology. It would provide a direct glimpse into the moment when the first supermassive black holes began their frantic growth, a window into the initial conditions that set the stage for everything that followed. Were their seeds the result of direct collapse, as many theorists suspect, or did they spring from the remnants of the very first unimaginably massive stars? The light from such an object would hold the answer, its spectrum a pristine record of a universe still untarnished by the complex chemical enrichment of later stellar generations. These future discoveries will do more than just break distance records. They will allow us to test the very laws of physics under conditions that are impossible to replicate on Earth. By studying the gravity around these earliest black holes, we can probe the limits of general relativity. By analyzing the subtle properties of their light, we can continue to test whether the fundamental constants of nature have truly remained constant over 13 billion years. Every new, more distant quasar is a fresh laboratory for fundamental physics, a natural experiment conducted on a cosmic scale. The journey to find them is a testament to humanity's insatiable curiosity, our relentless drive to understand our origins and our place in this vast, magnificent, and ever-revealing cosmos. The story of the most distant quasars is far from over. In many ways, it is just beginning. And so we reach the end of our expedition, having traveled across 13 billion years to uncover the secrets of the universe's most distant powerhouses. We began this journey peering at star-like points of light, only to discover they were the brilliant, beating hearts of infant galaxies, each one a supermassive black hole feasting in a cosmic frenzy. We learned that their incredible light is a time capsule, showing us the universe in its raw, formative youth, and that their very existence challenges our understanding of how gravity can build billion solar mass titans in the blink of a cosmic eye. From their role as lighthouses illuminating the cosmic web to their ability to launch galaxy-scale winds that shape entire galactic destinies, we have seen that quasars are far more than distant curiosities. They are the fundamental architects of the cosmos, active participants in the story of how everything we see, including the galaxy we call home, came to be. Every single fact we have explored is a vital piece of a grand, interconnected puzzle. The staggering growth of early black holes forces us to reconsider the seeds of cosmic structure. Their brilliant luminosity acts as both a creator and a destroyer, triggering star formation in one breath and quenching it in the next. The sophisticated techniques we use, from analyzing redshifted light to measuring the echoes of X-ray flares, all reveal a universe that is dynamic, violent, and beautifully governed by laws we are only just beginning to map with precision. These 50 insights are not a random collection of trivia. They are the chapters of a single, unified narrative about cosmic evolution, a story where gravity, light, and time intertwine to build the complex universe we inhabit today. The puzzle is vast, and while we have placed many crucial pieces, the full picture is still emerging, promising even more revelations as our technology and understanding continue to advance. This journey, however, does not end here. It continues every time a new observation is made, every time a theory is refined, and every time a curious mind looks up at the night sky with a sense of wonder. And that is where our final call to action lies. The next time you find yourself beneath a clear, dark sky, look up, past the familiar constellations, past the hazy band of the Milky Way. Let your imagination travel to the profound darkness between the stars. Remember that in what seems like an empty void, there are unimaginable powerhouses shining from the edge of time itself. their light a testament to the universe's turbulent and magnificent history. Our quest to understand them, to read their stories written in ancient light, is one of humanity's greatest adventures, and it is a story that is still being written. We would love to continue this exploration with you. Of the 50 incredible facts we journeyed through today, which one reshaped your understanding of the cosmos the most? Was it the realization that we are looking back in time, the baffling speed of early black hole growth, or the sheer power of relativistic winds? Share your most mind-bending moment in the comments below. Let's discuss the wonders that connect us all to this vast, beautiful universe. If you enjoyed this cosmic voyage, make sure to subscribe and hit the notification bell so you don't miss our next adventure into the mysteries of space, from the enigmatic nature of dark matter to the search for life beyond Earth. The cosmos is full of stories waiting to be told, and we